What if everything you thought was permanent and unchanging in the universe wasn't so permanent after all? Picture this. You wake up one morning and the world feels different. Gravity seems weaker, almost as if you could float off the ground with a single step. Light moves slower, casting long, distorted shadows that shouldn't be possible. The stars above might not even be where they were last night. This isn't a scene from a science fiction film. It's a real scientific possibility if the fundamental constants that govern our reality began to drift. These constants, like the speed of light or the strength of gravity, are the silent, invisible rules that keep our universe predictable and stable. But what if they weren't so constant? What if the laws of physics themselves could shift over time? Today, we're venturing into one of the most profound and unsettling ideas in modern cosmology, the concept of drifting constants. We'll explore what it would mean for atoms to lose their stability, for stars to burn differently, and for life as we know it to hang in the balance. This isn't just abstract theorizing. Scientists and philosophers are actively debating this possibility, drawing on evidence from the far reaches of space and the deepest principles of quantum reality. It challenges not only our understanding of the cosmos but our very place within it. By the end of this journey, you'll see the universe in an entirely new light, and you might never take the steady rhythms of nature for granted again. Together, we'll uncover why this idea captivates some of the greatest minds of our time and how it forces us to rethink everything from the formation of galaxies to the nature of existence itself. This is more than a scientific exploration, it's a journey into the heart of reality, and it's one you won't want to miss. So settle in, open your mind, and let's dive into the astonishing risk of a universe that changes its rules. At the heart of every physics textbook, every equation scrawled on a chalkboard, lies a set of numbers so fundamental we rarely even stop to question them. These are the fundamental constants, the immutable pillars upon which our entire understanding of the universe is constructed. Think of them as the unchanging rules of a cosmic game, the fixed settings on the control panel of reality. The speed of light in a vacuum, often denoted by the letter c, is a staggering 299,792,458 meters per second. And this value is not just a speed limit, it's woven into the very fabric of spacetime itself, dictating how energy and mass relate in Einstein's famous equation. Then there's Planck's constant, a tiny number that governs the bizarre and probabilistic world of the quantum, determining the size of everything from the energy of a photon to the uncertainty of a particle's position. And we can't forget the gravitational constant, which sets the strength of the force that holds planets in their orbits and shapes the large-scale structure of the cosmos. For centuries, the assumption has been that these values are not just constant across space, but fixed for all time. They are the unwavering standards against which we measure everything else. This belief isn't just a convenient starting point. It's the bedrock of the scientific method. The entire premise of repeatable experimentation hinges on the idea that the rules don't change between today and tomorrow, or between a lab in London and one on a distant exoplanet. We trust that a chemical reaction will proceed the same way, that a star will evolve according to predictable patterns, because the underlying constants are locked in place. This constancy allows us to peer back in time, using the light from galaxies billions of light years away, confident that the physics governing that ancient light is the same physics we study here on Earth today. It provides a stable foundation, a sense of order and predictability in a vast and often chaotic cosmos. But what if that foundation isn't as solid as we think? The revolutionary and frankly unsettling idea is that these constants might not be truly fundamental in the sense of being handed down by some immutable law. Instead, they could be more like frozen accidents, the outcome of how our particular universe cooled and settled into its current state following the Big Bang. And if they emerged from a process, could that process itself be dynamic? Could these numbers be slowly ticking away, changing at a rate so infinitesimally slow that our instruments have yet to definitively catch them in the act? The implications of even the tiniest shift are staggering to contemplate. A minuscule change in the strength of the electromagnetic force, governed by the fine structure constant, could prevent atomic nuclei from holding together, making the formation of carbon, the essential element for life as we know it, impossible inside stars. The cosmos would be stillborn, filled with hydrogen and helium but devoid of the complex chemistry needed for planets and life. A drifting gravitational constant could rewrite the history of the universe itself. If gravity was stronger in the past, the initial expansion from the Big Bang might have been overcome, causing the entire cosmos to collapse back in on itself in a big crunch before galaxies ever had a chance to form. If it were weaker, matter might never have clumped together to form those first stars, leaving the universe a cold, dark, and empty void. The delicate balance that allowed for our existence appears to be incredibly fine-tuned, and the notion that these dials could be turning, even slightly, challenges our deepest understanding of reality. It suggests a universe that is not a static arena governed by eternal laws, but a dynamic, evolving entity whose very rules are subject to change. This exploration forces us to ask not just how the universe works, but why it works this way in the first place, setting the stage for a profound rethinking of everything we thought we knew. Yet this assumption of perfect constancy, which feels so natural to us today, was not always the universal starting point for scientific inquiry. The very notion that these fundamental numbers might be capable of change has a rich and fascinating history, one that stretches back to some of the most brilliant minds of the 20th century. It's a story that reminds us that science does not advance in a straight line, but through a series of bold questions, spirited debates, and occasional wrong turns that ultimately lead to a deeper understanding. Long before we had the technology to probe the edges of the cosmos for evidence, there were thinkers who looked at the mathematical elegance of the universe and wondered if its settings were truly locked in place for all eternity. One of the most prominent early voices was the British physicist Paul Dirac, a Nobel laureate and one of the founders of quantum mechanics. In the 1930s, Dirac was struck by what he called large number coincidences. He noticed that certain ratios of fundamental constants, like the ratio of the strength of the electromagnetic force to the gravitational force between two protons, resulted in an enormous number around 10 to the power of 40. Even more curiously, he found that this number seemed to be of the same order of magnitude as the age of the universe expressed in fundamental time units. To Dirac, this was too significant to be mere chance. He proposed what became known as the large number hypothesis, suggesting that these enormous coincidences could be explained if the gravitational constant, g, was not actually constant, but instead decreased very slowly over the lifetime of the universe. In his view, gravity might be weakening as the cosmos expands, a revolutionary idea that directly challenged the bedrock of physics. This proposal did not go unchallenged. The scientific community, including figures of immense stature like Albert Einstein, was largely skeptical. Einstein himself had built his theory of general relativity on the foundation of immutable constants, and the idea of a drifting G was seen by many as unnecessary and unsupported by evidence. The renowned astronomer Sir Arthur Eddington also wrestled with these large number coincidences but pursued different explanations, seeking a more fundamental theory that would derive the constants from first principles rather than allowing them to vary. The debate between these giants of physics was not merely academic, it was a clash of philosophical worldviews. On one side was a desire for a perfectly static and eternal set of laws, and on the other, a growing intuition that the universe might be more dynamic and interconnected than previously imagined. For decades, Dirac's hypothesis remained on the fringes, a curious footnote in physics textbooks. The technology to test such a subtle change, a variation potentially as small as 1 part in a billion per year, simply did not exist. Scientists lacked the precise atomic clocks, the space-based telescopes, and the sophisticated laser systems needed to measure these effects across cosmic distances and time scales. Without empirical evidence, the idea languished, a beautiful but unproven speculation. Yet it never completely disappeared. It simmered in the background, inspiring a handful of researchers who saw in it a potential key to unifying the two great pillars of modern physics, general relativity and quantum mechanics. This historical context is crucial because it shows that our current investigations into drifting constants are not a sudden break from tradition, but rather the modern culmination of a question that has intrigued scientists for nearly a century. It is a powerful reminder that progress in science often requires us to re-examine our most deeply held assumptions, to dare to ask if the immutable might, in fact, be mutable after all. So how do we move from philosophical speculation to tangible evidence? The search for answers takes us from the chalkboards of theorists to the frontiers of observational astronomy, where scientists are actively hunting for clues imprinted on the fabric of the cosmos itself. This isn't about wild guesses, it's a meticulous, data-driven detective story that relies on some of the most advanced technology ever built. The primary method involves using the universe as a giant time machine. By looking at incredibly distant objects, we are effectively looking back in time, because the light from those objects has been traveling across space for billions of years to reach our telescopes. If the fundamental constants were different in the past, that light might carry a faint, telltale signature of that difference. The most compelling and controversial evidence comes from studies of the fine structure constant, that crucial number which dictates the strength of electromagnetic interactions. A team of astronomers, most notably led by John Webb, has spent decades analyzing the light from some of the most luminous objects in the distant universe, quasars. These are incredibly bright galactic cores powered by supermassive black holes. As the light from a quasar travels through clouds of interstellar gas on its way to Earth, specific elements in those clouds, like iron, magnesium, and zinc, absorb light at very precise wavelengths. These absorption lines act like a unique fingerprint for each element. The exact position of these lines in the spectrum is exquisitely sensitive to the value of the fine structure constant. It's like having a cosmic barcode that only scans correctly if the constants are exactly right. By comparing the barcodes from these ancient gas clouds, seen when the universe was just a fraction of its current age, to the barcodes we measure in laboratories on Earth today, Webb's team found something astonishing. Their data suggested that billions of years ago, in certain directions of the sky, the fine structure constant was slightly smaller than it is now. We're talking about a change of just a few parts in a million over billions of years, an almost imperceptible drift. But in the precise world of fundamental physics, even a shift that tiny is monumental. It would mean the rules of chemistry and atomic physics were subtly different in the past. This wasn't a single observation. It was a statistical trend seen across hundreds of measurements using the world's most powerful telescopes, like the Keck Observatory in Hawaii and the Very Large Telescope in Chile. Of course, a claim this extraordinary requires extraordinary evidence and is met with intense scrutiny. Other research teams have attempted to replicate these findings, some supporting the idea of variation and others finding no evidence at all. The measurements are at the very limit of our technological capabilities, and potential systematic errors, tiny biases in the instruments or in the analysis methods, are incredibly difficult to rule out entirely. It's a fierce and ongoing scientific debate. Beyond the quasar studies, other lines of evidence are being pursued. For example, the Oclo Natural Nuclear Reactor in Gabon, Africa, a place where 2 billion years ago, geological conditions accidentally created a self-sustaining nuclear fission reaction, acts as a natural prehistoric laboratory. By analyzing the precise ratios of radioactive elements left behind in the reactor's remnants, scientists can constrain how much the constants could have changed since that reaction occurred. So far, the Oclo evidence generally supports the constancy of constants, adding another layer of intrigue to the mystery. These investigations, whether they ultimately confirm variation or not, have already profoundly changed the conversation. They have forced physicists to take the idea seriously and to design ever more precise experiments to test it. We now have atomic clocks so accurate they would lose less than a second over the entire age of the universe, and scientists are comparing them over years to see if the tick rate of time itself, which depends on fundamental constants, is changing. We are probing the cosmic microwave background radiation, the afterglow of the Big Bang, for any imprint of different physics in the very early universe. Each of these efforts is a testament to a new way of seeing the cosmos, not as a static stage with fixed rules, but as a potentially evolving and dynamic entity where the very laws of nature might have a history of their own. Of all the fundamental numbers that shape our reality, few hold as much quiet power as the fine structure constant. Represented by the Greek letter alpha, this number is a pure, dimensionless constant, approximately equal to 1/137. It doesn't have units like meters or seconds. Its value is simply a ratio, a fundamental measure of the strength of the electromagnetic force. This is the force that governs how light and matter interact, and alpha is the dial that controls its intensity. It determines how tightly electrons are bound to an atomic nucleus, the energy required for chemical reactions to occur, and the very stability of matter itself. Without a fixed value for alpha, the predictable world of atoms and molecules we depend on would simply not exist. To grasp its profound influence, consider something as simple as a neon sign. The specific, vibrant red glow it emits is caused by electrons in neon atoms jumping between precise energy levels, releasing photons of a very particular color of light. The exact wavelength of that light, its place in the spectrum, is exquisitely sensitive to the value of the fine structure constant. If alpha were even slightly different, the energy levels within the atom would shift, and that iconic red would be a different color entirely. This principle is the foundation of spectroscopy, the science that allows astronomers to identify the chemical composition of stars and galaxies billions of light years away. We can do this because we assume the atomic physics operating in those distant stars is the same as the physics in our labs. But if alpha were drifting over cosmic time, that fundamental assumption crumbles. The spectral lines we observe from ancient galaxies would be subtly shifted in a way that couldn't be explained by motion alone, suggesting the very rules of atomic interaction were different in the past. The stakes become astronomically higher when we look inside the hearts of stars. The fine structure constant is a silent but crucial architect of stellar nucleosynthesis, the process that forges the elements of the periodic table. Inside the immense pressure and heat of a star, alpha governs the rate of nuclear fusion reactions. Most critically, it controls a fantastically precise and delicate process known as the triple alpha process. This is how stars create carbon, the essential building block of life as we know it. In this process, 3 helium nuclei must come together in a specific, resonant energy state to form a carbon nucleus. This resonance is like a perfectly tuned note on a musical instrument. If the energy levels within the atomic nuclei are even slightly off, the note falls flat, and the reaction fails or proceeds far too slowly. The strength of the electromagnetic force set by alpha directly determines these energy levels. If alpha were slightly larger, meaning a stronger electromagnetic force, the repulsion between the positively charged helium nuclei would be greater, making it harder for them to get close enough to fuse. The resonance would be lost and carbon production would plummet. If alpha were slightly smaller, the resonance might also be misaligned, or other alternative fusion pathways might dominate, potentially preventing the formation of heavier elements like oxygen altogether. A universe with a drifting alpha might be a universe where stars burn out without ever creating the carbon needed for planets, oceans, or living organisms. It would be a cosmos rich in hydrogen and helium but eternally barren, incapable of the rich chemistry that gives rise to complexity and ultimately us. This isn't just abstract theory. It's a demonstration of the breathtaking fine-tuning that allows our universe to be hospitable. The fine structure constant isn't merely a number on a page. It is quite literally a key that unlocks the potential for life itself, and the suggestion that this key could be turning in the lock is one of the most profound and humbling ideas in all of science. Now, let's turn our attention to a constant so fundamental we rarely even think about it, yet it literally holds our world together, the gravitational constant known as G. This is the number that sets the strength of gravity itself, the invisible glue of the cosmos. It appears in both Newton's law of universal gravitation and Einstein's theory of general relativity, acting as the precise dial that determines how powerfully masses attract one another. For centuries, we've built our understanding of the universe on the assumption that G is, and always has been, a fixed value. But what if that dial is slowly, imperceptibly turning? What if the force that keeps your feet on the ground and the Earth in its orbit around the Sun is not a permanent feature of reality, but a fading echo from the Big Bang? The consequences of a weakening gravitational constant would rewrite the history and future of everything we see. Let's start close to home with our own solar system. The delicate balance of planetary orbits is a cosmic dance choreographed by gravity. The Sun's immense mass creates a gravitational well, and the planets are like marbles rolling around its curved inner surface. The exact speed and distance of each orbit is a perfect equilibrium between the Sun's gravitational pull and the planet's forward momentum. If G were to decrease over time, the strength of that pull would gradually diminish. It would be as if the Sun's mass were slowly shrinking. The immediate effect would be that the planets would begin to spiral outward, their orbits expanding. While this might sound like a gentle, almost imperceptible change, the long-term effects would be catastrophic. A larger orbit means a longer year, and more critically, a significant drop in the amount of solar energy reaching each planet. For Earth, this would trigger a profound and irreversible ice age. As our planet drifted further from the Sun, global temperatures would plummet. The complex systems of life that have evolved over billions of years, perfectly adapted to a specific Goldilocks zone of temperature and light, would face extinction. The oceans would freeze, and the atmosphere itself could condense and fall as snow. Our world would become a frozen, lifeless rock adrift in an ever more distant orbit. This isn't just a thought experiment. It's a direct physical consequence of tampering with the most basic force governing celestial mechanics. The stability we take for granted is a gift of a constant g. On a grander scale, the very architecture of galaxies would be thrown into chaos. Galaxies are held together by the gravitational pull of their combined mass, which includes not only the stars we can see, but also the vast halos of mysterious dark matter. A weakening G would loosen this gravitational grip. The elegant spiral arms of galaxies like our own Milky Way would begin to unravel. Stars on the outer edges would gain enough energy to escape the galaxy's pull entirely, streaming off into the intergalactic void as lonely orphans. Within galaxies, the delicate dance of binary star systems would fall out of sync, and star clusters would dissipate. The universe would slowly but surely become a much darker and more lonely place, its structures dissolving over cosmic time. Perhaps the most bizarre effects would be reserved for the most extreme gravitational environments, black holes. The properties of a black hole, its event horizon, its density, its very existence are directly determined by gravity's strength. If G were to decrease, a black hole's event horizon, the point of no return, would actually shrink. In a sense, the black hole would weaken, its gravitational grasp becoming less absolute. Matter that was once irrevocably trapped inside might find itself on the other side of a retreating horizon, though the exact physics of such a scenario is a complex and mind-bending puzzle for theorists. Furthermore, the Hawking radiation that theoretically causes black holes to evaporate would be intensely affected, potentially speeding up their demise dramatically. The most stable objects in the universe could become transient phenomena. Finally, a drifting G has direct and dramatic implications for the fate of the entire cosmos. The expansion rate of the universe is a titanic tug of war between the outward momentum of the Big Bang and the inward pull of gravity from all the matter and energy in the cosmos. Much of our modern cosmology, including the discovery of dark energy, is built on the assumption that G is constant. If gravity is slowly fading, it would act as a phantom accelerator for the universe's expansion. The inward pull would be diminishing, meaning the outward expansion would begin to win the battle even more decisively. This could lead to a Big Rip scenario, where the expansion not only continues forever but accelerates to the point where it tears apart galaxies, solar systems, and even atoms themselves in the distant future. The constant we rely on to hold the universe together could, if it changes, be the very agent of its ultimate dissolution. This profound connection between the microcosm of atomic constants and the macrocosm of galactic evolution shows us that the rules of the game are deeply interconnected, and changing just one can unravel the entire tapestry of reality. But what about the ultimate speed limit itself, the cosmic constant that seems most absolute? The speed of light in a vacuum, 299,792,458 meters per second, is more than just a number. It is the linchpin of Einstein's theory of relativity, the unwavering constant C that weaves together space and time into a single fabric. This speed defines the very concept of causality, the principle that cause must always precede effect. It sets the maximum velocity at which any information, any influence, any signal of any kind can travel through the universe. It is the ultimate rule that keeps reality logical and ordered. The notion that this rule itself might not be a rule, that the speed of light could have been different in the past, challenges the bedrock of modern physics in ways that are almost difficult to comprehend. If the speed of light were not constant, the elegant equations of relativity would begin to fray at the edges. Time dilation, the strange effect where time passes more slowly for an object moving close to light speed, would become unpredictable. The precise calculations that allow us to synchronize the atomic clocks on GPS satellites with those on Earth would falter. Your phone's map application would quickly become useless, its accuracy dissolving as the satellite signals, which rely on the fixed speed of light to calculate position, arrived with timing that no longer matched our earthly expectations. The relationship between energy and mass, captured in history's most famous equation, E equals mc squared, would also transform. Since the energy output of a reaction is tied to the square of the speed of light, even a small decrease in c would mean that the Sun and every other star would generate vastly less energy, potentially plunging the cosmos into darkness and cold. A tiny increase could make nuclear reactions catastrophically more powerful. The implications reach back to the very beginning of everything. Some cosmological models, designed to solve puzzles about the early universe's uniformity, have proposed that light traveled significantly faster in the immediate aftermath of the Big Bang. This concept, known as variable speed of light cosmology, suggests that in the first fleeting fractions of a second, light could have moved so rapidly that it connected distant regions of the infant universe, allowing them to even out their temperature and density, which explains why the cosmos looks so similar in all directions today. After this initial burst, the speed would have dropped precipitously to the value we know and rely on. This isn't mainstream theory, but it is a serious proposal that highlights how questioning even our most sacred constants can open doors to solving deep cosmic mysteries. Our view of the cosmos would be fundamentally altered if c were variable. The cosmic horizon, the maximum distance we can see because light has had time to reach us since the beginning, would be a shifting, uncertain boundary. The age and size of the universe, which we calculate based on the constant speed of light, would become ambiguous moving targets. Astronomers looking at a distant galaxy would face a bewildering question. Is it truly that far away, or are we seeing it through a lens where the rules of the journey its light took have changed? Historical observations of stellar events like supernova, which we use as standard candles to measure cosmic distances, would be impossible to calibrate, throwing our entire understanding of the universe's expansion history into doubt. The speed of light is not just a number on a page. It is the steady heartbeat of our theoretical and technological world, the immutable rhythm that allows us to make sense of the cosmos from our small vantage point. Its constancy is the foundation upon which we have built our modern conception of reality, and its stability is something we depend on every time we look up at the stars or simply check our location on a screen. While the constants governing gravity and light shape the cosmos on a grand scale, there exists an even more fundamental layer of reality where another set of rules holds absolute sway: the quantum realm. This is the domain of Planck's constant, a number so small it seems almost insignificant, approximately 6.626 times 10 to the negative 34th joule seconds, yet it is the fundamental unit of action in the universe. This constant, denoted by the letter h, is the ultimate arbiter of the bizarre and counterintuitive world of atoms and subatomic particles. It sets the minimum possible amount of energy that can be exchanged. It dictates the scale at which quantum effects become dominant, and it is the very heart of Heisenberg's famous uncertainty principle, which states that you can never simultaneously know both the exact position and the exact momentum of a particle. The universe at this scale is not a deterministic clockwork mechanism but a probabilistic cloud of potentialities, and Planck's constant is the rulebook for that game of chance. Imagine, then, if this foundational rulebook began to rewrite itself, if Planck's constant were to drift, even by a seemingly negligible amount. The consequences would ripple upward from the quantum foam to dismantle our macroscopic world. The stability of every atom, the very building blocks of all matter we see and touch, is a direct consequence of a precise and unchanging H. Electrons orbit atomic nuclei not in neat planetary rings, but in specific quantized energy levels or shells. The exact size and energy of these shells are determined by Planck's constant. If H were to increase, these shells would expand outward, pushing electrons further from the nucleus and dramatically weakening the bonds that hold atoms together. Matter itself would become diffuse, ghost-like, its structural integrity dissolving. Chemical reactions which rely on the precise sharing or exchange of electrons between atoms would become unpredictable or simply cease to function. The DNA in your cells, a masterpiece of molecular engineering, would unravel as the hydrogen bonds holding its double helix together lost their strength. Life as a chemical process would be impossible. Conversely, if Planck's constant were to decrease, the quantum world would contract. Atomic orbitals would shrink, pulling electrons in much closer to the nucleus. This might sound like it would make matter more stable, but the opposite is true. The tighter confinement would drastically alter the energy required for chemical interactions. The delicate balance that allows for the vast diversity of organic molecules would be lost, likely resulting in a universe where only the simplest atoms could exist, forever trapped in a state of inert simplicity. The very process of photosynthesis, which powers nearly all life on Earth, relies on the quantum mechanical phenomenon of electron tunneling, a process exquisitely sensitive to the value of Planck's constant. A change here would shut down the primary engine of the biosphere, turning a vibrant green planet into a barren rock. This fragility extends to the cutting edge of modern technology. The entire field of quantum computing is predicated on our ability to manipulate quantum states with incredible precision. These states, known as qubits, are often defined by the spin of an electron or the energy level of an atom. Their stability and our ability to control them are entirely dependent on the constants of quantum mechanics remaining constant. A drifting Planck's constant would be akin to trying to build an intricate house of cards on a table that is subtly tilting back and forth. The quantum coherence that allows a quantum computer to perform its miraculous parallel calculations would collapse into noise and decoherence, rendering the machine useless. Our aspirations for a quantum-powered technological revolution would vanish into the uncertainty we sought to harness. The true lesson here is that the quantum world is not some distant, abstract domain separate from our own. It is the foundation upon which our reality is constructed. The solidity of the floor beneath your feet, the light from your screen reaching your eyes, the electrical signals racing through your brain as you comprehend these words. All of these everyday experiences are emergent properties of an underlying quantum reality governed by fixed, reliable rules. A change in those rules wouldn't just alter some obscure laboratory measurement. It would unravel the tapestry of existence thread by thread from the atoms upward. It demonstrates that our classical, predictable world is a magnificent and delicate emergence, a stable pattern dancing on a sea of quantum uncertainty, a pattern that depends entirely on the constants of that sea remaining perfectly, unwaveringly still. So where do these radical ideas even come from? How can a serious physicist propose that the very bedrock of reality might be shifting beneath our feet? It turns out that the concept of drifting constants isn't just wild speculation. It emerges naturally from some of the most sophisticated and ambitious theoretical frameworks ever devised in our quest to understand the cosmos. These aren't ideas that break the rules, they are attempts to discover deeper, more fundamental rules from which our familiar constants naturally arise. At the forefront of this quest is string theory, a candidate for the long-sought theory of everything that aims to unite gravity and quantum mechanics into a single, coherent description of nature. In the world of our everyday experience, we perceive 3 dimensions of space and 1 of time. But string theory suggests that to make the math work, to finally harmonize these 2 great pillars of physics, the universe must actually have many more dimensions, perhaps 10 or 11 in total. These extra dimensions are thought to be curled up or compactified into shapes so incredibly tiny that they are completely hidden from our view, existing at a scale billions of times smaller than an atom. This is where the magic and the potential for variation comes in. In string theory, the values of the constants we observe in our 4-dimensional world are not handed down by divine decree. Instead, they are determined by the specific geometry and size of these hidden, compactified dimensions. Think of it like a cosmic organ with many pipes. The notes you hear, the constants like the speed of light or the strength of gravity, depend on the length and width of the pipes. Now, if the geometry of these extra dimensions is not permanently fixed, if it can evolve or vibrate in different ways over the immense span of cosmic time, then the notes we hear, the fundamental constants, could change along with it. The dials on the control panel of reality would be connected to the dynamic behavior of these deeper structures. This provides an elegant and mathematically rigorous mechanism for why constants might drift. They are not truly fundamental, but are rather emergent properties of a deeper, more complex reality that is itself dynamic and evolving. Another compelling framework comes from modifications to Einstein's theory of gravity itself. While general relativity has passed every test thrown at it with flying colors, it famously does not play nice with quantum mechanics. Some physicists have proposed that to bridge this gap, we might need to allow the gravitational constant, g, to be not a fixed number but a dynamical field, much like the electromagnetic field. This idea is central to a class of theories known as scalar tensor theories, the most famous of which is the Brans-Dicke theory. In this view, the strength of gravity can vary from place to place and from time to time, mediated by a new particle or field that permeates all of space. The value of g we measure here and now would just be the current value of this field in our corner of the universe. These theories are not invented arbitrarily. They are serious attempts to solve deep theoretical puzzles, and they naturally predict that what we call constants might actually be slowly varying cosmological quantities. What's truly fascinating is that these theories don't propose a lawless, chaotic change. Any variation would presumably be governed by its own set of equations, its own underlying principles. The constants wouldn't be changing randomly or capriciously. They would be evolving according to a deeper, more fundamental law that we have yet to fully uncover. This turns the entire problem on its head. Instead of asking, why are the constants constant, we are led to ask, what is the law that governs how they change? This shift in perspective is monumental. It transforms constants from immutable inputs into observable outputs, turning them from static rules into dynamic players in the cosmic story. These theoretical frameworks provide the mathematical language to explore the what-if without descending into pure fantasy, offering a scaffold on which we can hang the tantalizing clues gathered from quasars and atomic clocks. They show us that the quest to understand constant drift is not a sideshow in physics, but a central pathway in our ongoing effort to hear the universe's deepest, most hidden harmonies. This incredible possibility that the very dials of reality might be slowly turning leads us to one of the most profound and mind-expanding concepts in all of modern cosmology, the multiverse. If the constants of nature are not fixed by some ultimate, universal law, but are instead more like local settings or environmental conditions, then our entire universe could be just one single region within a far vaster and more diverse cosmic landscape. The multiverse hypothesis transforms the unsettling idea of drifting constants from a terrifying anomaly into a natural, even expected, feature of reality. It suggests that what we have long considered to be the immutable and necessary laws of physics might be nothing more than the accidental bylaws of our particular cosmic neighborhood. Imagine a vast, infinite ocean with each bubble rising to the surface representing a separate, self-contained universe. In this cosmic foam, the process that births each bubble, perhaps a series of endless inflationary expansions, also sets the initial conditions within it. The way the bubble forms and cools could determine the geometry of its hidden dimensions, the strength of its forces, and the values of its fundamental constants. In one bubble universe, the gravitational constant might be set strong, causing it to collapse back in on itself almost instantly in a fiery big crunch. In another, the electromagnetic force could be too weak for atoms to ever form, leaving it a forever featureless sea of subatomic particles. Our universe, with its seemingly perfect Goldilocks constants that allow for galaxies, stars, planets, and life, is just one bubble among countless others, one where the random roll of the cosmic dice happened to land on a habitable combination. This is where a powerful philosophical idea, known as the Anthropic principle, comes into sharp focus. It simply states that we can only observe a universe that is capable of producing observers. We shouldn't be surprised to find ourselves in a universe with constants fine-tuned for life, because in a multiverse where the constants take on every possible value, we could not possibly exist in the overwhelming majority of them. We are here because this universe, by pure chance, had the right recipe. The others, the ones with gravity too weak to form stars or with nuclear forces too strong to allow for complex chemistry, are utterly barren and empty. There is no one there to be disappointed by the outcome. This principle doesn't explain why our constants have the values they do in a deep fundamental sense, but it does explain why we see the values we do. It naturalizes the apparent fine-tuning, suggesting it is not evidence of divine design, but rather a consequence of a vast and varied cosmic lottery. The implications of this view are both humbling and exhilarating. It challenges the very core of scientific methodology, which has always sought unique, fundamental laws that explain why things must be the way they are. Instead, the multiverse suggests that many properties of our world might be pure historical accidents, frozen into place during the birth of our local cosmos. It forces us to reconsider our place in the grand scheme of things. We are not the center of a single, purpose-built universe, but perhaps just fortunate inhabitants of one particularly hospitable island in an infinite archipelago of realities, most of which are bizarre, hostile, and utterly uninhabitable. This perspective doesn't diminish our universe. It makes the fragile, beautiful balance that allowed for our existence seem all the more precious and remarkable. Now, let's pull back the lens to see the full cosmic picture, to understand how these subtle shifts in the rules wouldn't just alter atoms or planets in isolation, but would rewrite the entire history and future of the cosmos from its very first moments. The universe as we know it is a grand, multi-billion-year story of structure emerging from chaos, a narrative written in the precise language of its fundamental constants. If that language began to change, the entire story would unravel into something unrecognizable, and the most profound casualty would be the potential for life itself. Consider the very first chapter of this story, the forging of the elements. In the first few minutes after the Big Bang, during the era known as Big Bang Nucleosynthesis, the entire universe was a scorching hot nuclear furnace. Protons and neutrons slammed together, frantically forming the first atomic nuclei. The outcome of this frantic process was almost entirely determined by the strength of the fundamental forces. The rate at which these reactions occurred, and the final abundances of elements like hydrogen, helium, and a tiny trace of lithium were exquisitely sensitive to the values of our constants. If, for instance, the strength of the strong nuclear force had been just a few % weaker in those first moments, the deuterium nucleus, a simple proton and neutron bound together, would have been far less stable. This would have acted as a catastrophic bottleneck. Without deuterium forming reliably, the entire chain of nuclear fusion would have stalled. The universe would have ended up almost entirely as hydrogen, with virtually no helium at all. This might seem like a minor detail, but it would have had a domino effect that changed everything. Later, when the first stars ignited, they would have had no helium fuel to burn, drastically altering their life cycles and the way they would eventually seed the cosmos with heavier elements. The cosmic palette available for building planets and people would have been impoverished from the very start. This brings us to the true cosmic engines of creation, the stars. Inside the crushing pressures and searing temperatures of stellar cores, the constants are the master architects of nucleosynthesis. The journey from hydrogen to the elements of life is a precarious tightrope walk, and the constants set the tension of that rope. We already touched on the triple alpha process and the creation of carbon, but the fine-tuning doesn't stop there. The next step is just as miraculous. For life to flourish, we don't just need carbon, we also need oxygen. Inside massive stars, carbon nuclei can fuse with another helium nucleus to form oxygen. This reaction is also governed by a precise resonance. If the strong nuclear force were even slightly stronger, the carbon-carbon fusion reaction would proceed much more rapidly. This might sound productive, but it would be disastrous. Stars would burn through their carbon fuel at a terrifying rate, converting almost all of it into heavier elements like neon and magnesium before they could ever expel it into space through a supernova. The universe would be rich in these heavier elements but critically deficient in both carbon and oxygen. There would be no carbon for organic molecules, no oxygen for water or breathable atmospheres. A universe with even a minor drift in these constants could easily become a universe without the two most fundamental elemental ingredients for life as we understand it. The implications cascade upward to the largest scales imaginable. The formation of galaxies themselves is a gravitational ballet, choreographed by the precise value of the gravitational constant and the initial conditions of the universe. If gravity were significantly stronger, the initial density fluctuations after the Big Bang would have collapsed into galaxies much more quickly and violently. This could lead to a universe dominated by enormous, chaotic elliptical galaxies, where stars are formed in frantic bursts, quickly using up their gas and leaving behind sterile systems. The stable, long-lived spiral galaxies like our Milky Way, with their quiet galactic suburbs perfect for nurturing life, might never form. Conversely, a weaker gravitational constant would mean matter would have a harder time clumping together at all. The cosmos might remain a vast, diffuse soup of gas, where the density never quite reaches the threshold to ignite the first stars. The universe would be a dark, empty void, forever waiting for a light that never comes. The large-scale structure of the cosmos, the beautiful cosmic web of filaments and clusters that we observe, is a direct signature of the strength of gravity. Change that strength, and you erase the signature, replacing it with an entirely different and likely far less interesting cosmic map. This breathtaking chain of causality, from the first 3 minutes to the formation of galactic superclusters, points toward an astonishing conclusion. Our existence hinges on a series of incredibly fortunate accidents. The constants of nature appear to be fine-tuned to an almost unbelievable precision within a very narrow window that allows for a complex, structured, and life-bearing universe. This realization connects the most grand and impersonal processes imaginable directly to you, sitting there watching this video. The carbon atoms in your body were forged in the heart of a long-dead star. The oxygen you breathe was a product of that star's precise internal physics. The calcium in your bones, the iron in your blood, every element heavier than lithium was crafted in stellar furnaces or in the violent explosions of supernova, all processes that depend critically on the constants having exactly the values they do. We are not just living in the universe, we are literally a product of its laws. If those laws were even slightly different, the stars would have produced a different set of elements, and the universe would be not just lifeless, but incapable of ever producing life. This isn't about finding life on other planets. It's about the very potential for chemistry complex enough to give rise to biology being written into the fundamental rules of reality. Our stable, predictable universe with its fixed constants appears to be a very special place, a cosmic sanctuary where the conditions were just right for the story of matter to eventually become the story of us. The hunt for drifting constants is a breathtaking feat of scientific ingenuity, a global effort that transforms a seemingly philosophical question into a problem of exquisite measurement. This isn't about gazing at the stars and merely wondering. It's about building instruments of such staggering precision that they can sense the universe's heartbeat changing over centuries. Scientists are essentially turning the entire Earth, and even the solar system, into a sophisticated laboratory to test the constancy of reality itself. One of the most precise methods involves the quiet, relentless ticking of atomic clocks. These are not ordinary timepieces. They are marvels of engineering that use the natural vibration of atoms, like cesium or strontium, as their pendulum. The frequency of these vibrations, the tick rate, is exquisitely sensitive to the values of fundamental constants, particularly the fine structure constant. The principle is brilliantly straightforward. If you place two identical, supremely accurate atomic clocks in different environments, say, one on Earth and one on a satellite, or even just two in different labs, and their tick rates begin to diverge over time in a way that cannot be explained by other factors, it could be a smoking gun for constant drift. Researchers have performed these comparisons over years, even decades, monitoring for any minuscule drift. The sensitivity is almost beyond comprehension. Some experiments are capable of detecting a change as small as 1 part in a billion per year. It's like being able to measure the slow, imperceptible widening of the Atlantic Ocean to within the width of a single atom. But why stop with a few years of data when the universe itself offers us a multi-billion-year-old laboratory? This is where ancient relics from space become critical time capsules. The Oclo Natural Nuclear Reactor in Gabon is a famous example, but meteorites can serve a similar purpose. These rocky travelers, some of which are older than the Earth itself, contain minerals that formed under precise radioactive conditions. By analyzing the isotopic ratios of elements like samarium or rhenium within them, scientists can effectively perform a forensic investigation into the strength of nuclear forces billions of years in the past. The decay rates of these radioactive isotopes are locked in a dance with fundamental constants. If the constants were different back then, the decay products we find frozen in the meteorite today would tell a different story than the one predicted by our current, unchanging laws. It's a direct test of physics across a significant fraction of cosmic history, using rocks that have fallen into our laps as silent witnesses to the ancient universe. The quest also stretches far beyond our planet, utilizing the grandest instruments we have built. The Very Large Telescope Array in Chile and other observatories like the Keck in Hawaii are on the front lines of the search. Astronomers use their immense light-gathering power to perform ultra-high-resolution spectroscopy on the light from impossibly distant quasars. As this ancient light passes through interstellar gas clouds, it creates those intricate absorption line barcodes we discussed earlier. By comparing the spacing between these lines in the ancient universe to their spacing in labs on Earth, researchers can hunt for any subtle shift that would betray a change in the fine structure constant. This work is a painstaking statistical marathon, requiring the analysis of hundreds of quasars across the sky to build up a signal strong enough to trust, pushing our telescopes and our analytical techniques to their absolute limits. Perhaps one of the most elegant experiments is happening right now, using a simple reflector left on the moon by Apollo astronauts decades ago. This technique, called lunar laser ranging, involves firing powerful laser pulses from observatories on Earth at these reflectors and precisely measuring the time it takes for the light to make the round trip. This distance, measured to within a few millimeters, is a direct test of gravity. Any change in the gravitational constant g would subtly alter the moon's orbit over time. By tracking the moon's precise position with this laser technique over many years, scientists can put incredibly tight constraints on how much g could possibly be changing. It's a beautiful synergy of space exploration, precision engineering, and fundamental physics, all aimed at answering one of the deepest questions we can ask. Each of these methods, from the quantum tick of an atom to the reflected glow of a laser from the moon, represents a different path up the same mountain, all converging on an answer to whether the rules of our universe are truly written in stone. This journey into the possibility of drifting constants does far more than challenge our physics. It strikes at the very core of our philosophical understanding of reality. For centuries, the scientific enterprise has been built on a foundation of what philosophers call metaphysical necessity, the belief that the laws of nature are not just descriptions of how things are, but eternal, unbreakable truths about how things must be. The force of gravity must follow an inverse square law. The speed of light must be the ultimate cosmic speed limit. This view, which can be traced back to thinkers like Immanuel Kant, posits that these laws are necessary features of any rationally conceivable universe. They are discovered, not invented, revealing a deep, pre-existing order that our minds are uniquely equipped to uncover. It's a profoundly comforting idea, suggesting that beneath the chaos of experience lies a permanent, intelligible structure waiting for us to decode it. But if the constants that underpin these laws can change, this entire edifice of necessity begins to crumble. It suggests that what we call the laws of physics might not be necessary truths at all, but rather colossal cosmic contingencies. They could be more like local bylaws or environmental conditions, the way the freezing point of water is a property of Earth-specific atmospheric pressure, not a universal rule. This shifts our perspective from a universe governed by eternal, transcendent logic to a universe where the rules are immanent, emergent, and perhaps even accidental. The German philosopher Gottfried Wilhelm Leibniz famously asked, "Why is there something rather than nothing?" The discovery of drifting constants would lead us to a similarly profound question. Why are the rules this way and not some other way? It forces us to confront the possibility that our universe's habitability is not the product of inevitable, preordained laws, but a breathtakingly fortunate roll of the dice in a cosmic casino with an infinite number of tables. This immediately plunges us into a deep debate about the nature of scientific knowledge itself. Is science the process of discovering a pre-existing, objective reality, or is it a process of inventing increasingly useful models to describe our subjective experience? If constants are fixed, science feels like a process of discovery. We are mapping the permanent contours of an external world. But if they drift, science begins to look more like a continuous act of invention and reinvention. Our models would not be final pictures of truth, but temporary maps of a landscape that is itself slowly shifting. This doesn't make science any less powerful or useful, but it does change its character. It becomes a dynamic conversation with a changing universe, rather than a monologue where we simply recite back eternal truths. It would humble the scientific endeavor, reminding us that our knowledge is always provisional, always subject to revision based on new observations of a universe that may not be playing by a static rulebook. This realization has a profound effect on human curiosity. The drive to understand the universe is often fueled by the hope of one day arriving at a final, complete theory, a theory of everything that would answer all fundamental questions. But if the rules themselves are in flux, the goalposts of understanding are always moving. This could be seen as a deeply frustrating prospect, dooming us to eternal ignorance. Yet, it could also be liberating. It transforms the cosmos from a static puzzle to be solved into an unfolding story to be participated in. Our curiosity would no longer be about uncovering a fixed set of secrets, but about engaging with an evolving narrative, learning the new rules as they emerge. It makes the scientific quest not a march toward a finish line, but an endless, wondrous exploration where the journey itself is the point. The universe becomes less like a clockwork mechanism and more like a living, breathing entity with a history and a future that is still being written, and our role shifts from passive observers to active participants in a grand, cosmic story of change. For millennia, humanity has looked to the heavens and found not chaos but order. The predictable cycles of the seasons, the unwavering paths of the planets, the fixed laws that govern reality, these have often been interpreted as the fingerprints of a divine architect, evidence of a cosmos built on a foundation of purposeful and eternal harmony. The very concept of unchanging physical constants resonates deeply with many religious and spiritual traditions, which have long seen in nature's regularity a reflection of a transcendent, steadfast intelligence. So what happens to this deeply held world when science introduces the radical notion that these constants might not be eternal decrees, but rather shifting sands? The idea of drifting constants doesn't just challenge physics. It opens a fascinating and respectful dialogue between scientific discovery and spiritual understanding, inviting us to reconsider ancient questions in a startling new light. Within many creation stories and theological frameworks, a universe governed by fixed, reliable laws is often seen as a direct expression of a creator's consistent and trustworthy nature. The unwavering speed of light or the perfect balance of gravitational force can be interpreted as manifestations of a divine plan, a cosmic order that allows life to flourish and human beings to comprehend their place within creation. This perspective offers a profound sense of comfort and meaning, suggesting that the universe is not a random accident but a carefully crafted home. The potential for these fundamental rules to change over time can therefore be initially unsettling from this viewpoint. It might seem to imply a capriciousness or instability in the very foundation of existence, challenging the idea of a universe purposefully designed with humanity in mind. For some, this could be perceived as a threat to faith, as if the solid ground of divine order is being replaced by the uncertain flux of random chance. Yet, many theological thinkers and religious traditions are not only adaptable to such scientific discoveries, but find within them new avenues for understanding the divine. Rather than seeing constant drift as evidence against a creator, some interpret it as a sign of a dynamic, ongoing creation, a universe that is not a one-time finished product but a continuously evolving masterpiece. In this view, a deity is not a distant watchmaker who wound up the universe and left it to tick on its own, but an ever-present participatory force, subtly guiding and shaping the cosmos through its very laws. The variation of constants could be seen as a form of divine artistry, a way of writing a more complex and dynamic story over billions of years. This aligns with process theology and certain interpretations within Hinduism and Buddhism, which emphasize a flowing, ever-changing reality as the fundamental nature of existence. The drift of constants becomes not a breakdown of order, but evidence of a living, breathing cosmos that is still being actively created. This conversation is beautifully mirrored in cultural narratives from around the world. Many ancient myths speak of a time when the world was different, when the sun was closer, when gravity was weaker, or when the laws of nature were not yet fixed. Aboriginal Dreamtime stories, for instance, tell of a formative era when ancestral beings shaped the landscape and established the laws of existence. These myths don't describe a static creation but a process of becoming, a concept that finds a surprising echo in the modern scientific hypothesis of evolving physical constants. They serve as a cultural touchpoint, reminding us that the human imagination has long grappled with the idea of a fluid reality, preparing us conceptually for the profound implications of modern cosmology. These stories provide a bridge, allowing us to approach a complex scientific idea not with fear, but with the recognition that it connects to a very ancient human curiosity about the nature of our world. The dialogue between these perspectives is not about one side winning and the other losing. It is about a richer, more nuanced understanding of both science and spirituality. Science gives us the tools to measure the potential drift of constants with astonishing precision, to test our ideas against the evidence of the cosmos. Spirituality and religion provide frameworks for grappling with the meaning of these discoveries, for asking the why questions that empirical data alone cannot answer. They ask what a dynamic universe implies for concepts like purpose, destiny, and human significance. Do we become mere accidental inhabitants of a universe with shifting rules, or does our ability to discover and ponder these very changes become a testament to a unique role within a grand, unfolding drama? The potential for constants to drift invites us all, whether we are guided by faith, reason, or both, to participate in a timeless human quest, to understand our place in a cosmos that is far more mysterious and wondrous than we ever imagined. Now, let's bring this cosmic speculation down to Earth in the most immediate and terrifying way possible. Imagine waking up tomorrow to a world where the fundamental constants have just begun their slow, inexorable drift. This isn't a distant billion-year process anymore. It's a crisis unfolding in real time. The first signs would be subtle, almost dismissible as glitches. Your smartphone might lose its GPS signal and never regain it, but this wouldn't be a simple satellite outage. It would be a fundamental breakdown of the technology itself. The entire global positioning system is a masterpiece of precision physics, reliant on the unwavering speed of light and the exact principles of general relativity. Atomic clocks on satellites, perfectly synchronized with those on Earth, constantly broadcast timing signals. Your phone or your car's navigation system calculates its position by measuring the minuscule time delay for those signals to arrive, a calculation that depends entirely on light speed being a constant 299,792,458 meters per second. If that number began to change, even by a tiny amount, the entire system would instantly become uncalibrated. The signals would arrive at slightly the wrong times, and the triangulation math would spit out coordinates that were completely wrong. You might be driving through Kansas while your dashboard insists you're in the middle of the Pacific Ocean. The entire global logistics network, shipping, air travel, military operations, financial timestamping would descend into chaos within hours, all because one constant decided to wobble. The chaos would quickly ripple outward from our communication networks into our energy infrastructure. The entire principle behind nuclear power, and indeed all energy production based on atomic reactions, would be thrown into question. A nuclear reactor is a precisely controlled environment where technicians maintain a stable chain reaction by carefully managing the behavior of neutrons. The probability that a neutron will cause a fission event, a value nuclear engineers spend their careers calculating, is exquisitely sensitive to the fundamental constants that govern the strong nuclear force. If those constants began to shift, the carefully balanced reaction inside a reactor core could suddenly become subcritical, shutting down entirely and causing widespread blackouts, or worse, it could become supercritical, leading to overheating and potential meltdowns. Power plants would have to be shut down immediately as a precaution, plunging cities into darkness and halting industry. But the problem wouldn't stop there. Even renewable energy sources like solar panels would be affected. The ability of a silicon cell to convert sunlight into electricity depends on the photoelectric effect, a quantum process governed by Planck's constant. A change there could render vast solar farms suddenly inert. Our entire civilization, which hums on a grid of perfectly predictable energy, would be starved of power, pushing society toward a pre-industrial state almost overnight. Perhaps the most viscerally terrifying effect would be the instability introduced to the force we feel every moment of every day, gravity. We take for granted that a dropped glass will fall to the floor and shatter, that our hearts can pump blood against a consistent gravitational pull, and that the ground beneath our feet will firmly support us. If the gravitational constant g began to decrease, that certainty would evaporate. At first, it might feel exhilarating, like a permanent moonwalk, but the novelty would quickly curdle into horror. Construction and engineering are disciplines built on the assumption of a fixed gravitational acceleration of 9.8 meters per second squared. The structural integrity of every building, every bridge, every dam on the planet is calculated based on this unshakable fact. A weakening gravity would mean that the tensile strength of steel cables, the load-bearing capacity of concrete pillars, and the very friction that holds bricks together would be radically altered. Skyscrapers that were once stable might begin to sway dangerously in winds they were designed to withstand. Bridges could groan under loads they were never calculated to carry in a lower G environment. The entire built environment of humanity would become a death trap, its safety codes suddenly obsolete. Our own bodies, evolved over eons for Earth-specific gravity, would struggle. Our cardiovascular systems, our bone density, even the very way our inner ear maintains balance could begin to malfunction, leading to widespread dizziness, fainting, and injury. The world would not only be falling apart around us, but we would be falling apart within it. This cascade of failure highlights a vulnerability we rarely consider. We prepare for earthquakes, pandemics, and solar storms, but we base all our disaster preparedness on a single, silent assumption that the rules of the game will not change. Our civilization is not just built on the Earth, it is built into the very laws of physics themselves. The microchip in your computer, the antibiotics in your pharmacy, the synthetic fibers in your clothing, all are products of a deep and precise understanding of a stable, reliable physical reality. A drifting constant would be the ultimate systemic risk, a vulnerability for which there is no backup plan, no redundancy, and no recovery protocol. It would be a reminder that for all our technological prowess, we are ultimately tenants in a universe whose lease terms we do not fully control, living on the goodwill of cosmic forces that have, until now, remained mercifully constant. This brings us to one of the most profound and unsettling questions this entire exploration forces us to confront. If we were to detect with certainty that a fundamental constant had begun to drift, what on Earth or beyond it should we do about it? The scientific and philosophical shock would be immense, but it would immediately be followed by an ethical crisis of unprecedented scale. We are talking about a scenario where humanity, a species that has existed for a mere blink of the cosmic eye, might discover it has the potential to not just alter its environment, but to literally reset the dials on reality itself. The sheer audacity of such a proposition is staggering. It forces us to grapple with the ultimate question of human agency. Are we merely passengers on a cosmic journey, or could we, in some distant future, become its stewards or even its mechanics? The first and most immediate ethical dilemma would be the classic problem of the precautionary principle on a universal scale. Any attempt to fix a constant, to nudge a fundamental force of nature back to its previous value, would be the most dangerous experiment ever conceived. Our entire understanding of physics is built upon the stable foundation we are trying to manipulate. It would be like trying to repair the foundation of a skyscraper while you are still living inside it, using blueprints that might become invalid with every turn of the wrench. A miscalculation, even a tiny one, could have cascading and catastrophic consequences we cannot possibly foresee. We might stabilize the fine structure constant only to accidentally cause a runaway collapse in the weak nuclear force. The ethical imperative to do no harm would suggest that the most moral course of action is one of extreme caution, perhaps limited to observation and study rather than active intervention. The risk of making things immeasurably worse might simply be too great to justify any action at all. On the other hand, a policy of non-intervention carries its own immense ethical weight. If we knew with high confidence that the drift would inevitably lead to the dissolution of atoms, the death of stars, and the ultimate extinction of all life, would we not have a moral responsibility to at least try to prevent it? This transforms the issue from a scientific curiosity into the ultimate existential risk mitigation project. The philosopher Nick Bostrom has argued that preventing human extinction is an overriding moral priority because of the vast, unborn future generations whose potential would be lost forever. This logic could be extended to all life in the universe. If we are the only intelligent species capable of recognizing and potentially countering this threat, our inaction could doom not just ourselves, but any other civilization that might arise in the future. The weight of that responsibility, the burden of being the universe's potential guardians, is almost too heavy to comprehend. This leads directly to a brutal and practical debate about resource allocation. The technological and intellectual effort required to even comprehend how to manipulate a fundamental constant would be the most ambitious project in human history, dwarfing the Apollo program or the Large Hadron Collider. It would demand a global commitment of trillions of dollars, the brightest minds across multiple generations, and the focus of our entire scientific and industrial capacity. Yet, while we are gazing at the cosmos, trying to solve a problem that may not manifest for millennia, there are urgent, immediate suffering and existential threats here on Earth: climate change, pandemic preparedness, poverty, and conflict. Is it ethical to divert vast resources to a speculative, long-term cosmic insurance policy when children are starving today? This is not an easy choice. It pits our responsibility to the present against our responsibility to the far future, forcing us to decide whether we are a species that merely survives day to day or one that plans for its cosmic legacy. Ultimately, the question of intervening with the constants of the universe forces us to define what it means to be human in a vast and possibly unstable cosmos. Are we humble inhabitants, accepting the universe's terms as they are given? Or are we active participants, with a growing duty to use our knowledge to preserve and protect the flame of consciousness? There are no easy answers here, only deeply uncomfortable trade-offs between arrogance and apathy, between caution and courage. This ethical maze shows us that the challenge of drifting constants isn't just about physics. It's a mirror held up to our own values, our priorities, and our vision for what humanity could one day become. Despite the mind-bending challenges and profound implications we've explored, the story of drifting constants is far from over. In fact, we are standing at the threshold of a new golden age of discovery. The tools and technologies now coming online are transforming this philosophical puzzle into a rigorous experimental field, equipping scientists with an unprecedented ability to peer into the deepest workings of the cosmos and finally answer the question, are the rules truly written in stone? This isn't a passive waiting game, it's an active global pursuit, a grand collaboration between theorists dreaming up new models and engineers building machines of exquisite sensitivity to test them. At the forefront of this effort are the next-generation observatories that will act as ultimate time machines. The James Webb Space Telescope is already revolutionizing our view of the early universe, but its work on constants is just beginning. By training its incredible infrared sensitivity on the most distant quasars, Webb can analyze the chemical fingerprints of ancient gas clouds with a clarity never before possible. It's not just about confirming or denying past claims about the fine structure constant. It's about mapping any potential variation across both time and space with a rich new dataset, searching for patterns that could reveal the underlying mechanism behind the drift. But the ambition doesn't stop there. Plans are already underway for even more powerful successors, like the extremely large telescope, which will have a mirror nearly half the size of a football field. Perched atop a mountain in Chile, this behemoth will collect enough light to perform spectroscopy on the first stars that ever formed, effectively allowing us to conduct a laboratory test of physics in the universe's infancy, pushing our empirical reach back to within a billion years of the Big Bang itself. While telescopes look outward, other projects are turning inward, using the principles of quantum mechanics to build impossibly precise sensors here on Earth. The field of atomic interferometry is creating devices that can measure the tiniest fluctuations in gravity, potentially sensing a change in the gravitational constant, g, in real time. These aren't massive machines, but increasingly compact and sophisticated labs where clouds of atoms are cooled to near absolute zero and used as exquisitely sensitive probes of the fundamental forces. By comparing the rate of ticks between different types of atomic clocks, some based on the vibrations of optical lattices, others on the transitions of a single ion, scientists can hunt for any divergence that would signal a change in the fine structure constant or the electron-to-proton mass ratio. These experiments run for years, building a record of such stability that they could detect a drift so small it would take 10 billion years for the constants to change by just 1%. Beyond our planet, space missions are being designed with this very question in mind. The Lunar Laser Ranging Experiment continues, but new proposals aim to place even more advanced reflectors on the Moon or even on Mars, creating a solar system-wide network for monitoring gravitational stability. There are even ambitious concepts for sending atomic clocks on deep space missions, far from Earth's gravitational influence, to see if time itself flows differently elsewhere, a direct test of fundamental physics that could only be done beyond our own backyard. Each of these projects, from the gigantic to the microscopic, represents a different path up the same mountain, all converging on a clearer picture of our universe's foundational stability. The theoretical work is keeping pace with ideas from string theory and quantum gravity generating new, testable predictions. The concept of the action, a hypothetical particle that could be both the source of dark matter and a field that causes constants to oscillate, is a prime example. If such a field exists, it wouldn't cause a constant linear drift, but a gentle, wave-like variation over millions of years. This kind of specific prediction gives experimentalists a new pattern to look for in their data, moving the search beyond a simple yes or no question and into the realm of detailed cosmic detective work. The synergy is powerful. A theorist's equation suggests a specific signature, and an observer then scours the data from a telescope or a quantum lab to find it. This back and forth is the engine of scientific progress, and it's running faster than ever before. What's truly inspiring is that this isn't a quest reserved for a small elite. It's a participatory human endeavor. The data from these monumental projects are increasingly made public, allowing astronomers and physicists from around the world to analyze them in novel ways. Citizen science initiatives sometimes allow amateurs to help classify quasar spectra or search for anomalies. This collective effort, spanning nations and disciplines, underscores a profound truth. The desire to understand our universe is a fundamental part of the human spirit. We are not just passive inhabitants of a cosmos with mysterious rules. We are active investigators, using our creativity and ingenuity to ask the biggest questions and build the tools to answer them. The journey to understand constant constancy is more than a technical challenge. It is a testament to our enduring curiosity and our unwavering optimism that the universe, however strange, is ultimately knowable. How do you even begin to explain that the universe's rulebook might be slowly rewriting itself? This isn't like teaching a new math formula or a historical date. It's about challenging the very bedrock of reality that students and all of us take for granted. The task of science communication here is monumental, but also incredibly exciting because it demands that we move beyond dry lectures and into the realm of immersive, imaginative experience. The goal isn't just to transmit information, but to cultivate a sense of profound wonder and flexible thinking, to prepare young minds not just for the science of today, but for the revolutionary discoveries of tomorrow. Imagine walking into a modern science museum, and instead of just seeing a static display on the periodic table, you step into an interactive exhibit called the Cosmic Tuning Fork. In the center of the room is a large tactile control panel with glowing dials, each labeled with a different fundamental constant: gravity, light speed, the strength of the electromagnetic force. As you turn a dial, the entire room responds in real time. Crank up the strength of gravity, and a holographic solar system projected above you shudders as planets spiral inward toward their star. Adjust the fine structure constant, and the vibrant colors of a nebula shift dramatically, its spectral lines blurring and reforming before your eyes. Turn the dial for the strong nuclear force, and a model of an atom, usually a stable, buzzing nucleus orbited by electrons, might either collapse into a dense lump or simply drift apart into a cloud of disconnected particles. This kind of visceral cause and effect demonstration makes an abstract concept tangible. It transforms the visitor from a passive observer into an active participant in a cosmic experiment, driving home the delicate balance of our universe in a way a textbook paragraph never could. In the classroom, teachers are harnessing the power of simple, powerful thought experiments that don't require a multi-million-dollar budget. A fantastic starting point is what's often called the "what if" game. Students are asked to consider a single, small change and then brainstorm the ripple effects across all of science and daily life. What if light traveled at the speed of sound? Suddenly, the setting sun would vanish from the sky instantaneously, not gradually. Satellite TV and internet would be impossible due to impossible lag times, and even turning on a light switch would leave you standing in darkness for agonizing seconds. What if gravity were 10 times stronger on Earth? Trees would be squatter and thicker, animals would be built like low-slung tanks, and the atmosphere itself would be denser, potentially creating a permanent, oppressive fog. These exercises aren't about getting the right answer. They're about building a muscle for systems thinking, helping students understand that physics isn't a collection of isolated facts, but a deeply interconnected web where tweaking one thread changes the entire tapestry. The digital world offers another frontier for exploration through sophisticated online simulations and massive open online courses, or MOOC. Platforms like PHET Interactive Simulations from the University of Colorado Boulder offer free, game-like tools where students can manipulate variables and instantly see the outcomes. While they might not have a specific drifting constants module, the principles are there: changing mass in a gravity simulation or altering energy levels in a quantum wave function. Dedicated online courses, often taught by leading physicists and cosmologists, can take curious learners on a deep dive, using animations and visualizations to illustrate complex theories like string theory's extra dimensions. These resources democratize access, allowing anyone with an internet connection to engage with cutting-edge ideas that were once confined to graduate-level seminars at elite universities. Perhaps the most crucial shift in educational outreach is the move away from presenting science as a fixed canon of undeniable truths and toward framing it as a dynamic, ongoing process of inquiry. Teaching about drifting constants is a perfect opportunity to do this. Educators can present the evidence from the Quasar studies and the counter-evidence from the Oclo Reactor, not as a confusing contradiction, but as a thrilling detective story where the final chapter hasn't been written yet. They can highlight the work of scientists like John Webb not as authorities handing down answers, but as explorers mapping the unknown. This approach does something vital: it humanizes science. It shows students that it's okay to not have all the answers, that debate and disagreement are the engines of discovery, and that they themselves could be the ones to eventually solve the mystery. It's about fostering a resilient curiosity that is comfortable with uncertainty and excited by the prospect of questions that don't yet have answers, ensuring the next generation is not just prepared to receive knowledge, but to challenge it and push it forward into uncharted territory. Now let's shift our perspective from the cosmic and philosophical to the intensely practical, to the very bedrock of our global civilization, the economy. We often think of markets as being driven by human decisions, resource availability, and technological innovation, but we rarely consider that they all rest upon a deeper, silent foundation: the unwavering laws of physics. Our entire modern economic system is a towering, intricate structure built on the assumption that the rules of the game are fixed. If those rules began to change, the resulting economic shockwaves would be immediate, severe, and utterly unprecedented, revealing a vulnerability we never knew we had. Consider the global financial markets, the high-speed nervous system of the world economy. This system operates on a concept so fundamental we barely think about it: precise, synchronized time. Every nanosecond counts in high-frequency trading, where algorithms execute millions of transactions based on microsecond advantages. This temporal precision is governed by atomic clocks, which in turn rely on the immutable vibrations of cesium atoms, a process dictated by the fundamental constants of quantum mechanics. If those constants began to drift, the very definition of a second would start to change. atomic clocks around the world would begin to tick at slightly different rates. The flawless synchronization that allows for secure global transactions would shatter. Timestamps on trades would become meaningless. Contracts could be invalidated due to impossible-to-determine sequences of events, and the entire multi-trillion-dollar edifice of international finance could descend into chaotic disputes and catastrophic losses almost overnight. The trust that enables money to move across the planet in the blink of an eye is ultimately trust in the stability of reality itself. The shock would then ripple outward into the realm of technology and manufacturing, striking at the heart of one of the most complex processes ever devised: semiconductor fabrication. Creating a microchip is an act of atomic-scale precision. It involves using light of a very specific wavelength dictated by the speed of light and quantum constants to etch circuits onto silicon wafers. These circuits are now so small that they consist of just a handful of atoms. If the fine structure constant were to drift, altering the behavior of electrons and the nature of chemical bonds, the entire process would fail. The light used in lithography machines would no longer have the correct properties to create sharp patterns. The doping processes that give silicon its semiconductor properties would become unpredictable. A factory worth billions of dollars could instantly find its entire production line yielding nothing but useless, malformed silicon. The global supply chain for everything from smartphones and cars to medical equipment and power grids would seize up, triggering an economic collapse that would make any previous recession look like a minor correction. Our world runs on silicon, and silicon runs on fixed physics. The energy sector would face its own parallel crisis. Our ability to generate power, whether from fossil fuels, renewables, or nuclear fission, is deeply rooted in predictable physics. A nuclear power plant is the most extreme example. The controlled fission reaction at its core is a carefully maintained balance, entirely dependent on constants governing nuclear forces remaining constant. Engineers calculate exactly how many neutrons will be released from each split atom to keep the chain reaction stable. A shift in these constants could cause the reaction to suddenly slow and stop, plunging regions into blackout, or worse, to rapidly accelerate toward a meltdown. Even renewable sources are not immune. The efficiency of solar panels, which convert photons to electricity through the photoelectric effect, would fluctuate if Planck's constant or the charge of an electron changed. The entire concept of a reliable energy grid, the engine of modern industry, would become a thing of the past, forcing a painful and rapid descent toward a pre-industrial existence. Finally, consider the ambitious and costly endeavors at the edge of human exploration, like space travel and satellite networks. Every single mission to another planet, every orbital calculation for a satellite, and every communication with a deep space probe is computed using Newton's and Einstein's equations, which are built upon the gravitational constant and the speed of light. These are not just abstract numbers in a textbook, they are active inputs in the guidance systems of every spacecraft. If the gravitational constant g began to decrease, the calculated trajectories for missions would be instantly wrong. A spacecraft headed for Mars might miss it entirely, flying off into the void. Multi-billion-dollar satellites in geostationary orbit, which must maintain a precise position to function, would begin to drift, colliding with each other and creating cascading fields of debris that would render entire orbital pathways unusable. The economic value of the orbital space around our planet, which enables global communications, weather forecasting, and Earth observation, would be utterly destroyed, setting our global connectivity back by decades. This practical angle reveals a stunning truth. Our economic prosperity and technological advancement are not just social constructs. they are a fragile harvest dependent on the stable and mercifully constant conditions of a universe that has, until now, always played by the same rules. But how does this profound shift in our cosmic context, this potential for foundational instability, actually land within the human mind? We are creatures of pattern and predictability, wired to find comfort in routine and certainty. The revelation that the universe itself might lack that ultimate certainty strikes at something very deep within our psychology, triggering a spectrum of responses that can range from paralyzing anxiety to transcendent awe. This isn't just an intellectual exercise, it's an emotional and existential journey that forces us to confront our place in a cosmos that is far less static than we ever imagined. Understanding these psychological effects is crucial, not to instill fear, but to equip ourselves with the tools to process this new reality in a healthy and ultimately empowering way. For many, the initial reaction to the idea of drifting constants is a deep, visceral anxiety, a form of cosmic-scale dread. Psychologists who study responses to existential threats like climate change or pandemics identify a phenomenon called ontological insecurity, a fundamental loss of trust in the stability of the world and one's place within it. This usually applies to the social or environmental order, but the concept scales up perfectly. Learning that the physical laws underpinning reality could be fluid can induce a profound version of this insecurity. The ground beneath your feet feels solid, but the knowledge that the force making it so could be weakening can make the world itself feel ephemeral, like a dream that might dissolve upon waking. This isn't a fear of a specific event, like an asteroid impact, but a diffuse anxiety about the very framework of existence becoming untrustworthy. It can lead to feelings of insignificance, a sense that if the universe's rules are arbitrary and shifting, then perhaps human striving, knowledge, and even love are ultimately meaningless in the face of such immense impersonal chaos. Yet, for a significant number of people, this exact same information sparks the opposite reaction, not anxiety, but a breathtaking and humbling awe. This aligns with what astronomers call the overview effect, a cognitive shift in awareness reported by astronauts who see Earth from space and are struck by its fragility and unity. The concept of a changing cosmos is a mental overview effect. It shatters a simplistic, mechanical view of the universe and replaces it with something far more dynamic and wondrous. Instead of a cold, static clockwork, we see a living, evolving, and incredibly creative process. This perspective can be deeply liberating. If the constants aren't fixed by some unchangeable decree, then the universe is not a pre-written script but an unfolding story, and our ability to observe and comprehend it becomes an even more remarkable part of that narrative. The awe comes from the realization that we are not just passive inhabitants of a finished cosmos, but active participants in a reality that is still being shaped, and that our consciousness is the universe's way of understanding its own evolving nature. The key to navigating between the poles of anxiety and awe lies in conscious coping strategies, in finding ways to hold this vast knowledge without being overwhelmed by it. One powerful approach is to actively cultivate a sense of wonder through continuous learning. Understanding the how and why behind these concepts can demystify them and replace fear with fascination. Following the work of scientists who are calmly and methodically testing these ideas, people who are not panicking but are instead driven by curiosity, can be incredibly reassuring. It reframes the narrative from one of impending doom to one of ongoing discovery. Another strategy is rooted in mindfulness and practices that ground us in the present moment and in our immediate sensory experience. While the constants might theoretically drift over billions of years, the coffee in your cup is still hot today, the laughter of a friend is still joyful now, and the sunset is still beautiful this evening. Anchoring ourselves in the concrete reality of our human-scale experiences provides a psychological balance to the abstract, cosmic scale of these ideas. It allows us to hold both truths simultaneously, that the universe may be fundamentally dynamic and that our lived experience within it remains real, valuable, and worthy of our full attention. This journey through our own psychological landscape reveals that the greatest challenge posed by drifting constants may not be scientific or technological, but deeply personal. It asks us to develop a new kind of cosmic resilience, a flexibility of mind that can accommodate profound uncertainty without collapsing into fear. It invites us to find a stable footing not in the illusion of an unchanging external reality, but within ourselves, in our capacity for wonder, our thirst for understanding, and our connections to each other. In doing so, we don't diminish the science, we complete it. We acknowledge that the quest to understand the universe is inextricably linked to the quest to understand ourselves and to find meaning and purpose, not in spite of the cosmos's mysteries, but precisely because of them. Long before physicists ever put pen to paper to calculate the potential variance of a fundamental constant, artists and storytellers were already exploring the emotional and psychological terrain of a universe without fixed rules. The human imagination has a remarkable ability to run ahead of scientific discovery, using the tools of metaphor, allegory, and sheer creative force to map out the contours of possibilities that science is only now beginning to test. This isn't a new phenomenon. For centuries, creators have instinctively understood that altering the basic premises of reality is one of the most powerful ways to explore what it means to be human, to question our place in the cosmos, and to process the anxiety and wonder that such questions provoke. Art becomes a vital sandbox for the soul, a safe space where we can experiment with the idea of instability without facing the actual consequences, allowing us to grapple with complex scientific concepts on an emotional level long before we can fully grasp them intellectually. Consider the surrealist painters of the early 20th century, like Salvador Dali or René Magritte. Their work deliberately warps the familiar constants of our everyday experience to create a dreamlike, disorienting effect. In Dali's The Persistence of Memory, time itself is the variable that has lost its constancy. The iconic melting clocks are more than just a bizarre image. They are a profound visual representation of time dilation, of a world where seconds ooze like syrup and the rigid, predictable ticking of a clock is replaced by a fluid, unreliable drift. Magritte's Golconda, which shows men in bowler hats raining down from the sky, plays with the expectation of gravity, presenting a scene where the force that anchors us to the ground has become merely a suggestion. These artists weren't physicists, but they were philosophers of perception, using their canvases to challenge the viewer's deepest assumptions about a stable, ordered world. They understood that by bending the rules of reality, they could bypass our logical minds and speak directly to our subconscious, evoking feelings of unease, curiosity, and awe that are remarkably similar to the emotions stirred by the scientific hypothesis of drifting constants. This tradition of bending physics found a natural home in the genre of science fiction, where writers have constructed entire narrative universes around a single, altered variable. A quintessential example is Philip K. Dick's novel Ubik, where the very nature of reality and the flow of time are in a state of constant, terrifying decay. Objects and people regress into earlier forms, and the protagonist must struggle against a universe whose rules are actively unraveling around him. It's a chilling and brilliant allegory for the anxiety of living in a world where nothing can be trusted to stay the same. On a different note, Isaac Asimov's classic story, The Gods Themselves, features a parallel universe where the strong nuclear force is stronger than in our own. Asimov doesn't just state this as a fact, He uses it as the foundational premise for an entire alien biology, society, and chemistry, imagining how beings would evolve and think in a world with fundamentally different physical laws. These stories do the heavy emotional lifting for science, taking a dry, technical concept like constant variation and exploring its human and non-human consequences, allowing us to feel the weight of the idea long before we understand the math behind it. This exploration has exploded into popular culture through films and video games, which offer an immersive, sensory experience of a fluid universe. Christopher Nolan's film, Interstellar, is a masterclass in this, particularly in its depiction of a planet orbiting a supermassive black hole where gravitational time dilation is so extreme that a few hours on the surface equate to decades passing elsewhere. The audience doesn't just hear about this concept, they feel its devastating emotional impact as a father returns from a short mission to find his daughter has lived an entire lifetime without him. The film takes a consequence of Einstein's theory of relativity and turns it into a powerful human drama about love, loss, and the unforgiving nature of time. In the realm of gaming, titles like Portal or Anti-Chamber are built entirely around playful, puzzle-based violations of standard physics. Players are handed a device that creates wormholes, breaking the conventional rules of spatial connection, or they navigate impossible, non-Euclidean spaces where hallways loop back on themselves and gravity shifts direction. Through interactive play, these games bake an intuitive understanding of alternative physics into the player's experience, making the bizarre and counterintuitive feel not only logical but fun. What all these creative endeavors share is a profound understanding that some truths are too large, too strange, or too frightening to be approached through data alone. They require story, symbol, and sensation. Art and creativity provide an essential translation service for the human spirit, converting the cold, abstract language of equations into the warm, relatable language of human experience. They allow us to confront the terrifying possibility of a universe without fixed rules from a position of safety, transforming existential dread into a source of wonder and intellectual adventure. By giving form to our deepest cosmic anxieties and aspirations, artists and storytellers don't just entertain us, they expand our emotional and intellectual capacity to engage with the universe's greatest mysteries, preparing our hearts and minds for the astonishing truths that science may one day reveal. This grand quest to understand the very bedrock of reality is a pursuit that no single nation, no solitary research institution could ever hope to undertake alone. It is a quintessentially human endeavor, one that demands we pool our resources, our intellect, and our curiosity across every imaginable border. The investigation into whether the universe's constants are truly constant is a stunning example of global collaboration in action, a symphony of synchronized effort where telescopes on distant continents act as a single instrument and data streams from every corner of the Earth are woven together into a coherent picture. This isn't just science, it's a powerful testament to our ability to set aside earthly divisions in pursuit of answers to the most profound questions we can ask. Consider the Very Long Baseline Interferometry Network, a project that embodies this spirit of unity. Here, radio telescopes scattered across the globe, from the high deserts of Chile to the mountains of Hawaii, from the plains of Spain to the outback of Australia, are electronically linked together to create a virtual telescope with a diameter as wide as the Earth itself. This allows astronomers to achieve resolutions so incredibly sharp they could spot a baseball on the surface of the Moon. But its purpose is far grander. By observing distant quasars and galactic cores with this unparalleled clarity, scientists can perform precise tests of fundamental physics, measuring how gravity bends light around massive objects and constraining any potential drift in the constants that govern those interactions. The data from each dish is useless on its own. It only gains meaning when combined with the signals from all the others. This requires an astonishing level of coordination, with each facility's atomic clocks synchronized to within a fraction of a nanosecond to ensure the signals can be perfectly aligned. It is a beautiful, silent dance of technology and cooperation, a daily demonstration that when we work together, we can see further and more clearly than we ever could apart. This collaborative spirit extends far beyond astronomy and into the world of immense particle accelerators like the Large Hadron Collider at CERN. This monumental machine is not a European project, it is a global one. Thousands of scientists from over 100 countries, representing a vast spectrum of nationalities, cultures, and languages, converge to design experiments, analyze results, and push the boundaries of what we know about the fundamental forces. While hunting for new particles is its most famous goal, the research conducted there also places incredibly precise constraints on the possible values and potential variability of the constants that shape our universe. The raw data generated is not hoarded by a single nation or corporation. It is made available to the worldwide scientific community, fostering an open and transparent environment where discovery is the only priority. In a world often fractured by political strife and competition, places like CERN stand as beacons of what is possible when humanity directs its collective intellect toward a common goal, proving that the language of mathematics and the scientific method can bridge any divide. This global network extends down to the most precise laboratories on Earth, where the hunt for constant drift is measured in the quiet ticking of atoms. To determine if the fine structure constant is changing, researchers don't just compare one clock to another in the same lab. They compare the most accurate clocks in the world, often separated by vast distances. A clock at the National Institute of Standards and Technology in the United States might be meticulously compared to its counterpart at the Physikalische Technische Bundesanstalt in Germany or the National Metrology Institute of Japan. These comparisons, conducted over fiber optic cables and via satellite links, require an unprecedented level of trust and cooperation between nations. They are essentially measuring the fundamental tick rate of time itself across continents, and any discrepancy could hint at a deeper cosmic truth. This isn't a competition to see who has the best clock. It is a shared mission to see what all the clocks together can tell us about the universe. It is a humble and powerful recognition that the quest for knowledge is a shared human inheritance, and its fruits belong to everyone. Now, let's clear the air and tackle some of the biggest misunderstandings that swirl around this mind-bending topic. When people first hear that the universe's constants might not be constant, it's natural for the mind to leap to some pretty alarming conclusions. The most common fear is that this means everything is random, that the cosmos is fundamentally chaotic and unpredictable, and that all of science is therefore built on quicksand. If the rules can change, how can we trust anything we think we know? This is perhaps the most important myth to bust right away. The idea of drifting constants does not mean a descent into lawlessness or cosmic anarchy. In fact, it implies almost the exact opposite. If constants were found to vary, they would almost certainly not be changing in a wild, random, or arbitrary way. Think of it not as the universe throwing the rulebook out the window, but rather as discovering that the rulebook has a few extra, previously hidden chapters that describe how the rules themselves can evolve over immense timescales. Any variation would be governed by a deeper, more fundamental law, a meta-law, if you will. Scientists wouldn't throw up their hands in defeat. They would lean in with intense curiosity to discover that new law. The variation itself would have a pattern, a rate, and a mechanism that could be studied, measured, and ultimately understood. It would transform constants from static inputs into dynamic outputs, but the process governing that change would itself be a consistent, studyable feature of reality. Science wouldn't become unreliable. Its mission would simply expand to include an even more profound layer of the universe's workings. A crucial clarification that helps untangle this confusion is the important distinction between a physical constant and a physical law. This is a subtle but critical difference that often gets blurred in popular discussion. A physical law is a descriptive statement about how nature behaves under given conditions. It's a principle like the law of conservation of energy or the second law of thermodynamics. These are the unchanging rules of the game. A physical constant, on the other hand, is a specific number that appears within the equations that describe those laws. It's a fundamental parameter, a fixed value that plugs into the rules. For example, the law of universal gravitation describes the relationship between mass, distance, and force. The gravitational constant, big G, is the specific number that quantifies the strength of that force. The concept of drifting constants suggests that these specific numerical values, these knobs on the control panel, might be tunable. But it does not mean the laws themselves are being broken. The law of gravity would still be a true description of how mass attracts mass. The strength of that attraction, set by G, might just be different in different epochs. This is a comforting distinction. It means the logical relationships that form the backbone of physics, the cause and effect, the conservation principles, the mathematical symmetries remain intact and reliable. We are not talking about a universe that behaves illogically from one moment to the next. We are talking about a universe whose settings might change on a cosmological clock, but whose underlying operating system remains coherent and intelligible. This understanding should reinforce our trust in the scientific process, not undermine it. It shows that science is a flexible, adaptive tool, perfectly capable of refining its models to encompass even the most astonishing new discoveries about the nature of reality itself. So after exploring these truly cosmic ideas, where does that leave you and me, right here, right now? It's one thing to intellectually grasp that the speed of light or the strength of gravity might not be forever fixed, but it's another to feel that knowledge, to let it settle in and actually change how you see your own life. This isn't just about physics. It's a deeply personal invitation to reconsider your perspective on time, your purpose, and your place in this vast and possibly fluid universe. Think about the way you experience time in your daily life, the frantic rush to meet deadlines, the slow, cherished moments with loved ones, the feeling that the years are slipping by. We often operate as if time is this external, constant ticking clock against which we measure our progress and our regrets. But what if that very tick is not quite as reliable as we thought? The possibility that the constants governing time itself could be in flux reframes our relationship with it. It suggests that time is not a rigid, external master, but a more malleable and intimate part of the cosmic fabric. This can be a liberating thought. Instead of feeling like you're racing against an unchanging clock, you might start to see your time as a unique and precious moment in an unfolding story. A story whose pace might be different elsewhere, but is yours to experience fully right here. This idea also touches on our search for purpose. Many of us look for meaning in things that feel permanent and enduring, building a legacy, creating art that lasts, or establishing truths that will hold for generations. The notion of drifting constants gently challenges that. It suggests that the universe itself might not be a permanent, static stage, but a dynamic, evolving entity. This doesn't render our lives meaningless, quite the opposite. It makes our brief, brilliant flash of existence seem even more miraculous and valuable. Your life, your consciousness, your ability to love and create and wonder, these are not small things happening on a small, stable rock. They are the universe in this particular corner and this particular moment becoming aware of itself. Your purpose isn't diminished by cosmic instability, it becomes more poignant. You are a part of the universe's great experiment, a conscious participant in its ongoing creation. The work you do, the kindness you show, the connections you forge, these aren't just entries in a ledger that will someday be complete. They are ripples in a much larger, ever-changing pond, contributions to a story that is still being written. To make this truly personal, let's try a simple exercise. Sometime today, find a quiet moment and ask yourself these questions, not to find a right answer, but to simply sit with the feeling they evoke. First, if you knew for certain that the physical laws of the universe were slowly changing, what is one thing you would see or experience that you've been putting off? Would you look at the stars more often? Would you finally take that trip to see the ocean? This question cuts through the noise of daily procrastination and connects you to a genuine desire for experience. Second, how does it feel to consider that the atoms in your hand, forged in the heart of an ancient star, are held together by forces that might not be absolute? Does that make you feel fragile, or does it make you feel deeply connected to a grand and dynamic cosmic process? And finally, if you could send a message to a future generation living in a universe with slightly different rules, what would you tell them about what it felt like to be alive in this precise moment, with the constants set exactly as they are? Your answers are yours alone, but the act of asking them transforms this from a distant scientific theory into a living part of your own narrative. It's in these personal reflections that the vast scale of cosmology meets the intimate scale of human life, reminding us that we are not just observers of the universe, but an active and meaningful expression of it. Deep in the heart of Gabon, Africa, lies a geological formation that sounds like something straight out of science fiction, yet it provides one of the most compelling pieces of real-world evidence in the debate over constant drift. This is the Oclo uranium deposit, and roughly 2 billion years ago, entirely through natural processes, it became the site of a self-sustaining nuclear fission reaction. For hundreds of thousands of years, this natural reactor quietly hummed away, its power moderated by groundwater seeping through the porous rock. It was a perfectly balanced, natural nuclear power plant operating long before any life form on Earth could even conceive of such a thing. When French physicists discovered the evidence for this in the 1970s, they found something astonishing preserved in the ancient rock, the nuclear waste. And it is this 2-billion-year-old waste that acts as a pristine, prehistorical laboratory, allowing us to run a critical test on the constancy of nature's most fundamental parameters. The test revolves around a specific nuclear reaction and a particularly finicky isotope called samarium-149. In any nuclear reactor, whether man-made or natural, one of the many byproducts of fission is a rare earth element called neodymium. The precise ratios of different neodymium isotopes found in the spent nuclear fuel are like a detailed receipt from the reaction, telling scientists exactly what reactions took place and how efficiently they proceeded. But one reaction is especially sensitive to the value of a fundamental constant: the capture of a neutron by a samarium-149 nucleus to become samarium-150. The likelihood of this capture happening, a value nuclear physicists call the cross-section, depends critically on a specific energy level within the newly formed samarium-150 nucleus. This energy level is not arbitrary. It is determined by the strength of the strong nuclear force, which is itself governed by the fundamental constants of particle physics. It's a direct, measurable link between the microscopic world of atomic nuclei and the grand constants that shape our universe. Here's where the detective work gets brilliant. Scientists can take samples from the long-cooled Oclo Reactor and measure, with incredible precision, the exact amounts of various neodymium isotopes left behind. They can then use our current, modern understanding of physics to run the nuclear reaction in reverse, so to speak. They ask a simple question: given the isotopic ratios we see today, what value must the neutron capture cross-section for samarium-149 have been 2 billion years ago for this particular reaction to have produced this specific nuclear waste signature? When they perform this calculation, the answer they get is astonishingly clear. The required value for that ancient cross-section is within a remarkably small margin of error, identical to the value we measure for it in nuclear physics laboratories today. The inescapable conclusion is that the physics governing nuclear reactions has not changed over the last 2 billion years. The fundamental constants that dictate the behavior of the strong nuclear force have remained locked in place, stable to within a few parts in 10 million over that immense span of time. This makes the Oclo Reactor a powerful check on the more tantalizing evidence from distant quasars. While the quasar data hints at possible variation in the fine structure constant governing electromagnetism over billions of years and across vast cosmic distances, the Oclo evidence acts as a local anchor. It tells us that here, in our own cosmic backyard, on a timescale of 2 billion years, the nuclear constants have not budged. This doesn't necessarily invalidate the quasar findings, but it places incredibly tight constraints on them. It suggests that if the fine structure constant is indeed varying, it is doing so at a rate so excruciatingly slow that its effect on nuclear processes over Earth's history is undetectable. The Oclo data is a sobering, grounding counterpoint, a reminder that extraordinary claims require extraordinary evidence, and that the universe often guards its deepest secrets with a consistency that we are only beginning to appreciate. This ancient African mine has become a silent witness for the prosecution in the case against constant drift, its testimony written not in words but in the immutable language of atomic isotopes. But how do we move from these grand, almost philosophical speculations to something concrete, something we can actually test and measure? The bridge between the terrifying "what if" and the rigorous "what is" built with the unshakable tools of mathematics. It is here, in the realm of equations and algorithms, that physicists and mathematicians collaborate to turn a mind-bending concept into a quantifiable model, creating simulated universes inside computers where they can tweak the dials of reality and watch what happens. This isn't about wild guessing. It's about constructing detailed, predictive frameworks that allow us to explore the consequences of drifting constants without having to wait billions of years for the results. At the heart of this effort are differential equations, the mathematical language of change itself. These are not simple algebraic formulas that spit out a single number. They are intricate sets of instructions that describe how a system evolves over time. Think of them as the ultimate recipe for reality. A standard cosmological model uses differential equations that have the fundamental constants baked into them as fixed parameters, like a cake recipe that always calls for exactly 2 cups of flour. To model a universe with drifting constants, mathematicians must rewrite these recipes. They introduce a new layer of complexity, treating the constants not as fixed numbers but as dynamic variables, themselves governed by their own equations. The gravitational constant g is no longer just a number in Newton's law. It becomes a function, g of t, where t is time. The fine structure constant alpha might be modeled as alpha of t, slowly evolving as the universe expands. This transforms the entire cosmological model from a static description into a dynamic, evolving story, with the equations capturing the intricate feedback loops between the expansion of the universe, the formation of structures, and the changing strength of the forces themselves. The complexity of these new models is so immense that they can only be solved through the brute force of computational mathematics. This is where supercomputers enter the stage, acting as digital laboratories for entire universes. Physicists program these machines with the modified differential equations, initializing them with the conditions of the Big Bang and then setting the constants on their prescribed paths of change. They might run thousands of simulations, one where gravity weakens by 1 part in a billion per year, another where the strong nuclear force strengthens slightly over time, and a third where multiple constants drift in concert. They then fast-forward the simulation through 13.8 billion years of cosmic evolution in a matter of days or weeks, watching intently to see what kind of universe emerges on the other side. Does it form galaxies? Do stars ignite and produce heavy elements? Or does it remain a featureless soup of hydrogen or collapse back in on itself prematurely? By comparing the outcomes of these simulated universes to the one we actually observe, researchers can effectively rule out entire classes of variation. If a particular drift scenario consistently produces a universe that looks nothing like ours, it's strong evidence that such a drift does not occur, or at least not at that rate. To make this abstract process relatable, consider a more familiar example: weather forecasting. Modern weather prediction is also a feat of computational mathematics. Meteorologists use complex models based on fluid dynamics and thermodynamics, feeding in initial data about current temperatures, pressures, and wind speeds. The model then simulates how these parameters will change over time, predicting the path of a storm or the arrival of a cold front. Now, imagine if one of the fundamental parameters in those equations, like the specific heat capacity of air or the latent heat of condensation, began to change over the course of the forecast. The model would have to account for that drift, and the predictions would become far more uncertain and complex. The challenge of modeling drifting constants is akin to this, but on a cosmic scale and with far higher stakes. It's like trying to predict the global climate not just for next week, but for the next billion years, while the very chemistry of the atmosphere is slowly transforming. This analogy helps demystify the process, showing that it's an extension of the same logical, computational thinking we already rely on to navigate our world, just applied to the most fundamental parameters of existence. This powerful synergy between abstract mathematics and raw computational power does more than just constrain theories. It actively guides the experimental search. A compelling simulation might predict that a specific type of constant drift would leave a unique fingerprint on the cosmic microwave background radiation, the afterglow of the Big Bang. This gives astronomers a very specific signal to look for in the incredibly precise data from telescopes like Planck. Instead of scanning the data for any anomaly, they can hunt for a specific pattern predicted by the math, making the search far more efficient and targeted. In this way, mathematics acts as a divining rod, pointing our limited resources and observational tools in the most promising directions. It transforms the search for drifting constants from a fishing expedition into a precise treasure hunt, with equations and algorithms drawing the map. This demonstrates the true power of mathematics, not as a mere accounting tool for nature, but as a prophetic language that allows us to peer into possibilities far beyond our immediate grasp, testing the stability of the cosmos itself from the quiet confines of a computer server room. Yet the implications of a shifting cosmos extend far beyond the abstract realms of cosmology and theoretical physics. rippling outward to transform entire fields of study we often consider separate. This is where the true power of interdisciplinary science shines, forging connections between seemingly distant disciplines to tackle a challenge that redefines them all. Consider biology, the science of life. Our entire understanding of evolution is built on the premise of a stable planetary stage with fixed physical rules. Life adapts to its environment through natural selection, but what if the environment itself includes the very laws of chemistry and physics? A drifting fine structure constant wouldn't just alter the universe around life, it would strike at the molecular machinery of life itself. Enzymes, the exquisite protein catalysts that enable every metabolic process in every cell, rely on their precise three-dimensional shape to function. That shape is determined by complex folding patterns, a delicate dance of electrical forces and hydrogen bonds that is exquisitely sensitive to the strength of the electromagnetic force. If that force began to change, even gradually over millennia, these essential molecules could misfold, becoming useless or even toxic. Photosynthesis, the foundational process that powers most of the biosphere, depends on the quantum mechanical process of electron transfer, a phenomenon governed by constants like Planck's constant and the charge of the electron. A shift here could reduce the efficiency of sunlight conversion to chemical energy, slowly starving the planet. Biologists and physicists are now collaborating on speculative models of alternative biochemistries, exploring how life might theoretically adapt to a world with different physical parameters. Could a species evolve a kind of error correction system at the molecular level to compensate for shifting atomic bonds? Would evolution speed up dramatically to race against the changing rules, or would life simply hit a wall and vanish? These aren't just thought experiments, they force us to reconsider the very definition of life and its resilience, pushing biology into a new cosmic context. This fusion of fields extends powerfully into the domain of computer science, where the challenge isn't just modeling a changing universe but building the tools to even conceive of it. Simulating the cosmos with static constants is already a task that pushes the world's most powerful supercomputers to their limits. Introducing drifting parameters adds a staggering new layer of complexity. Each calculation of a galaxy's evolution or a star's life cycle must now account for feedback loops where the changing constants alter the physics, which in turn alters the rate of change itself. Computer scientists are developing novel adaptive algorithms and neural networks that can learn and predict these non-linear dynamics, creating digital sandboxes where cosmologists can play out billions of years of cosmic history under different drift scenarios. These simulations are more than just video games, they are vital testing grounds. They allow us to ask which patterns of variation are even mathematically possible and consistent with the universe we see today. Furthermore, this research raises a profound question for the future of computing itself. The transistors at the heart of every computer chip operate based on the reliable principles of quantum mechanics. A drift in Planck's constant or the electron charge could, over vast timescales, threaten the very basis of digital logic, forcing computer scientists to theorize about entirely new forms of computation built for a universe that doesn't play by fixed rules. This collaboration is turning computer science from a mere tool for physicists into a full partner in the quest to understand reality's foundation. Perhaps most surprisingly, this cosmic question finds an urgent application in the seemingly grounded world of economics and long-term risk analysis. Economists are experts at modeling systemic risks, the cascading failures that can occur in global financial networks or supply chains. The concept of drifting constants introduces the ultimate systemic risk, a threat to the operational stability of reality upon which all human systems are built. Think of it as the deepest possible form of long-term portfolio management. How do we allocate resources today to mitigate a potential threat that may not manifest for millennia, but whose impact would be absolute? Economists and policy experts are beginning to work with physicists to develop frameworks for valuing cosmic stability, calculating the present-day economic value of ensuring a habitable universe for future generations. This involves bizarre but necessary calculations, like estimating the economic cost of a total collapse of digital infrastructure due to shifting semiconductor physics, or the cost of adapting global energy production if nuclear fusion becomes impossible under new physical parameters. This interdisciplinary dialogue forces us to expand our definition of existential risk beyond nuclear war or asteroid impacts to include threats from the fundamental fabric of existence, challenging humanity to think on timescales as vast as the cosmos itself and to consider our collective responsibility to the far future. Now, let's bring this cosmic speculation down to a conference room on Earth, where policymakers are forced to grapple with a question that feels like it's straight out of a science fiction novel. How does a government tasked with addressing the immediate needs of its citizens' healthcare, infrastructure, economic stability, justify allocating precious resources to prepare for a threat that may not manifest for millions of years, if ever? The debate over whether to fund research into drifting constants or even develop contingency plans forces us to confront the most profound challenges of long-term thinking and collective responsibility. This isn't an abstract philosophical exercise. It's a practical dilemma about how we, as a society, choose to navigate a future filled with deep and fundamental uncertainty. On one side of this debate is the compelling argument for investment in basic scientific research. Proponents would point out that the very technologies we rely on today, from the global positioning system in our phones to the medical imaging that saves lives in hospitals, are the direct results of curiosity-driven research into fundamental physics that once seemed equally esoteric. Investigating the constancy of constants is not a frivolous pursuit. It is the deepest possible form of due diligence. By funding the telescopes, atomic clocks, and supercomputers needed for this research, we are essentially taking out an insurance policy on our entire understanding of reality. The premium is a tiny fraction of a national budget, but the potential payout is the continued stability of the technological civilization we've built. Furthermore, this research doesn't happen in a vacuum. The technological spin-offs from pushing the boundaries of precision measurement often lead to revolutionary advances in other fields, from more accurate medical diagnostics to new materials science. The argument is that you cannot predict which piece of pure research will yield the next world-changing technology, so the wisest policy is to cultivate a broad and deep scientific ecosystem, trusting that the pursuit of knowledge for its own sake will ultimately provide its own practical rewards. However, this perspective inevitably clashes with the harsh realities of political and budgetary cycles. A politician facing re-election every few years must demonstrate tangible results to their constituents: new roads, better schools, lower taxes. It is incredibly difficult to campaign on the promise of having funded an experiment that might, in a decade, tell us that a fundamental constant is stable to 1 part in a quintillion. The immediate, visceral needs of the present, alleviating poverty, combating climate change, improving health care, understandably take precedence over a speculative risk whose timeline is measured in millennia. Critics of significant investment might argue that it represents a misallocation of scarce resources, a luxury that a world grappling with urgent crises cannot afford. They might ask, should we really be spending millions on monitoring the gravitational constant when millions of people lack access to clean water? This is not a cynical question. It is a moral and practical one that highlights the brutal trade-offs inherent in governance. This viewpoint champions a policy of vigilant observation but minimal intervention, prioritizing resilience and adaptability in the face of any future change rather than attempting to predict or prevent the unpredictable. Between these two poles lies a more nuanced and perhaps more sustainable approach: the integration of extreme long-term thinking into our existing frameworks for risk management and public education. We already have government agencies dedicated to preparing for low-probability, high-impact events. Think of FEMA planning for catastrophic natural disasters or health organizations developing protocols for pandemic response. The concept of drifting constants could be incorporated into this broader category of existential risks, not as an immediate priority, but as a scenario worth monitoring and understanding. This wouldn't require a massive diversion of funds, but rather a slight broadening of perspective within institutions that are already considering the far future, such as environmental protection agencies or departments of energy. The policy wouldn't be to build a gravity-stabilizing machine, but to ensure that our scientific monitoring networks are robust and that our understanding of the threat is continuously refined. Perhaps the most critical policy consideration of all is public education. A society that is scientifically literate and comfortable with concepts of deep time and cosmic scale is better equipped to engage in these difficult conversations without succumbing to either panic or apathy. The goal wouldn't be to frighten people, but to foster a sense of informed stewardship, educational curricula that include not just the facts of science, but the process of science, including its unanswered questions and ongoing debates, can cultivate a new generation that thinks critically about the long-term future. This shifts the burden from a handful of policymakers to a more engaged and thoughtful populace, creating a cultural foundation that supports measured, rational investment in our cosmic future. It's a policy of preparing the mind rather than just preparing the budget, ensuring that as our knowledge evolves, our society has the wisdom to decide what to do with it. This approach bridges the gap between the individual's sense of wonder about the universe and the collective's responsibility to safeguard the future, turning a terrifying cosmic possibility into a catalyst for deeper thinking and more meaningful dialogue about the legacy we wish to leave. Behind every great scientific leap, you will find not just a brilliant idea, but a person with the courage and tenacity to challenge the established way of thinking. The search for drifting constants is no different. It is a story powered by human curiosity, and few embody this spirit more than the astronomer John Webb. In the late 1990s, Webb and his team began analyzing the light from distant quasars, not to study the quasars themselves, but to use them as cosmic lighthouses, their beams illuminating ancient gas clouds billions of light-years away. The goal was audacious: to see if the fingerprints of atoms in those clouds, their spectral lines, were slightly different from those measured in laboratories on Earth. This was a painstaking, meticulous process, like trying to detect a single wrong note in a symphony played across the universe. The early data from the Keck Observatory in Hawaii hinted at something extraordinary: a tiny but persistent shift in the fine structure constant. Rather than immediately announcing a universe-altering discovery, Webb's reaction was one of intense skepticism. He and his team spent years methodically searching for any possible error in their instruments, their analysis, or their assumptions. They knew that claiming such a fundamental finding would invite intense scrutiny, and they were determined to scrutinize their own work more fiercely than any critic ever could. The scientific community's reaction was exactly as expected, a mix of fascination and profound doubt. Other researchers attempted to replicate the findings, some supporting the idea and others finding no evidence at all. The debate grew heated at times, a healthy if sometimes uncomfortable part of the scientific process. Through it all, Webb maintained a focus not on winning an argument, but on pursuing the truth. He didn't dig in his heels. He and his collaborators expanded their search, gathering more data from the other side of the planet using the Very Large Telescope in Chile. Astonishingly, the southern sky data seemed to tell a different story, or perhaps a more complex one, suggesting the variation might not be uniform across the entire universe. Instead of seeing this as a setback, Webb saw it as a new puzzle, a deeper layer of mystery to be unraveled. His career demonstrates that a true scientist is not defined by being right, but by an unwavering commitment to following the evidence wherever it may lead, even if it leads to more questions than answers. This intellectual honesty in the face of ambiguity is the very heart of the scientific spirit. John Webb's story is inspiring, but he stands on the shoulders of other courageous questioners. Decades earlier, the physicist Paul Dirac, already a Nobel laureate for his work in quantum mechanics, was captivated by what he called large number coincidences. He noticed that certain ratios of fundamental constants resulted in enormous numbers that seemed curiously related to the age of the universe. To Dirac, this was too significant to be mere chance, and he proposed a radical idea. The gravitational constant might be slowly decreasing over time. This was a heretical suggestion from a man of his stature, directly challenging the bedrock of Einstein's theory of general relativity. Many of his peers, including the great Arthur Eddington, dismissed the idea. Without the technology to test it, Dirac's hypothesis remained a mathematical curiosity, but it planted a crucial seed. It showed that even our most deeply held assumptions are worthy of examination, and that sometimes the most profound questions are asked not by outsiders, but by the very masters of the field. Dirac's courage to question, even at the risk of his own reputation, helped create a space for later innovators like Webb to explore these possibilities. These stories are not just history, they are a living testament to the human qualities that drive discovery. It is the perseverance to continue a decades-long search for a signal buried in unimaginable noise. It is the resilience to accept criticism and use it to strengthen one's own work. And it is the humility to admit that the universe is far more complex and wondrous than any single theory can encompass. This process is not a straight line from question to answer. It is a winding path of failed ideas, unexpected results, and collaborative breakthroughs. By sharing these human struggles alongside the brilliant successes, we demystify science. We see that it is not a cold, robotic process, but a deeply human endeavor fueled by passion, curiosity, and a shared desire to understand our place in the cosmos. These researchers remind us that the greatest tool in science is not a telescope or a particle accelerator, though those are vital, but the courageous and questioning human mind, forever willing to look at the familiar and ask, what if it were different? The most incredible part of this entire cosmic mystery is that you don't need a billion-dollar telescope or a particle accelerator to join the investigation. The quest to understand the constancy of our universe is one of the most democratic scientific pursuits imaginable, and there are powerful ways for anyone with any level of background to become an active participant in this grand exploration. This isn't about just watching from the sidelines. It's about rolling up your sleeves and contributing to a real scientific effort that is actively shaping our understanding of reality itself. One of the most direct and impactful ways to get involved is through citizen science projects. Platforms like Zooniverse host a myriad of projects where researchers need the human eye and brain to help them analyze vast datasets that computers still struggle with. Imagine sitting at your computer and being presented with the actual light spectra from distant quasars. the very data that astronomers like John Webb used to hunt for changes in the fine structure constant. Your task might be to help identify and mark the specific absorption lines from elements like iron or magnesium. You're not just playing a game, you're processing real information that could help confirm or refine our models of the early universe. Each classification you make becomes a tiny piece of a massive crowdsourced puzzle, helping professional scientists sift through information at a scale they could never manage alone. It's a profound feeling, knowing that your curiosity and a bit of your time could genuinely contribute to one of the biggest questions we can ask. If you're more inclined toward a hands-on experiment, you can turn your own home into a laboratory to test the consistency of physical laws. A beautifully simple yet powerful project involves building a basic pendulum. All you need is a weight, some string, and a way to measure time. The period of a pendulum, the time it takes to swing back and forth, is governed by a simple formula that depends on its length and the strength of gravity. If the gravitational constant g were to change, even by a minuscule amount, the pendulum's swing would gradually speed up or slow down over time. By constructing a precise pendulum and measuring its period over weeks or months, you are essentially conducting your own long-term test of gravitational constancy. To get useful data, you'll need to control for other variables like temperature changes that could affect the string's length, which introduces you to the meticulous and careful world of experimental design. This project connects you directly to a history of scientific discovery. It was with pendulums that scientists first began to precisely measure the force of gravity centuries ago, and now you can continue that tradition from your living room. For those who love to explore through simulation, the digital world offers incredible resources. Websites like PHET Interactive Simulations, run by the University of Colorado Boulder, offer free, browser-based tools that model physical phenomena. While they might not have a specific drifting constants module, you can experiment with the principles that underpin the idea. You can manipulate variables in gravity and orbit simulations or alter parameters in quantum wave function models to see firsthand how sensitive our reality is to the exact values of its settings. For a more advanced experience, there are open-source cosmology simulation codes available for download. Running these on a home computer allows you to tweak the underlying constants in the software and watch a virtual universe evolve over billions of simulated years. You can see for yourself how a slightly stronger electromagnetic force might prevent galaxies from forming, or how a weaker gravity would lead to a cold, diffuse cosmos. These simulations transform abstract concepts into visceral, visual experiences, making the fine-tuning of our universe strikingly clear. The journey doesn't have to stop there. Amateur astronomy clubs are fantastic places to learn how to conduct spectroscopic analysis. With a modest telescope and a commercially available spectrometer attachment, you can capture the light from bright stars and even planets, breaking it down into its constituent colors to see the unique fingerprint of its chemical composition. You can then compare your results to standardized databases, checking for the consistent patterns that tell us the rules of atomic physics are the same here as they are light years away. Engaging with this community connects you with others who share this deep curiosity, creating a network of enthusiasts who support and learn from each other. Every time you look through a telescope, you are conducting a test across time and space, verifying that the laws of physics holding your world together are the very same laws that govern the light from a star that left its surface thousands of years ago. This hands-on engagement transforms you from a passive consumer of knowledge into an active steward of discovery, proving that the greatest scientific instrument we have is, and always will be, our own innate human curiosity. And so we reach the end of our journey, a voyage that has taken us from the immutable equations in our textbooks to the edge of a cosmos that might be fundamentally fluid. We've stood alongside astronomers analyzing the ancient light from quasars, peered into the remnants of a 2-billion-year-old natural nuclear reactor, and grappled with the staggering possibility that the dials on reality's control panel could be slowly, imperceptibly turning. This isn't just a theoretical exercise, it's a profound re-examination of everything we thought was permanent. The very atoms that constitute our bodies, the stars that light the night sky, and the forces that hold it all together. Each depends on a delicate balance of numbers we assumed were fixed for all time and space. To question their constancy is to question the stage upon which the entire drama of existence plays out. Yet, this exploration leaves us not with a sense of despair, but with a renewed and even deeper appreciation for the incredible cosmic sanctuary we find ourselves in. The mind-bending fine-tuning required for a universe that can generate carbon, foster life, and give rise to conscious beings who can look back and wonder at it all is nothing short of miraculous. Whether this balance is a fortunate accident in a vast multiverse, a divine blueprint, or something beyond our current comprehension, the result is the same, a reality that allows for us. The potential for drift doesn't cheapen our existence. It makes the stable epoch we are living through seem all the more precious, a golden age in the cosmos's long history where the conditions were just right for wonder to flourish. Our ability to even conceive of these ideas, to build instruments precise enough to test them, is a powerful testament to human curiosity and resilience. We are the universe becoming aware of itself, and part of that awareness is daring to ask if its own rules are negotiable. This quest, driven by a handful of curious minds across generations, shows that science is not a static set of facts but a living, breathing process of inquiry. It's a conversation with the cosmos, one where we must be humble enough to let go of our most cherished assumptions and brave enough to follow the evidence, no matter how unsettling the path may be. As this conversation continues, with next-generation telescopes and quantum sensors set to probe deeper than ever before, we all have a role to play. Stay curious, ask big questions, marvel at the fact that we can use the laws of physics to test the laws of physics itself. Let this knowledge change your perspective, not by fostering anxiety, but by expanding your sense of wonder. The next great discovery could come from a team of researchers analyzing data, or it could be sparked by a new way of thinking from someone just beginning their journey into these mysteries. The cosmos is not done revealing its secrets, and the greatest chapters in our understanding of reality are likely still unwritten. So keep looking up, keep wondering, and never stop exploring the incredible, mysterious, and perhaps